Okay, I wanted to welcome everybody to this webinar sponsored by the Regulatory Assistance Project. I'm going to be muting your phones so that you can't interrupt the presentation until we have questions, but we have questions scheduled throughout the proceedings here, so you'll have plenty of time to ask questions. We are going to be asking you to give us some feedback after this seminar, and the way to do that is if you want to, at any time, you can either wait till the end of the seminar, or at any time if you have to leave the seminar, you can click on the red button at the top right there with an X. There's a white X on a red circle, and that will take you directly to a survey which will give you a quick Survey Monkey, about 10 questions to answer with respect to what you learned and how you thought the presentation went. This project is brought to you essentially by the Regulatory Assistance Project and the Energy Foundation. It's going to be roughly 3 hours of give and take seminar, and Tom Eckman and myself, my messenger from ITron, are going to be providing you with the best of our knowledge about essentially two topics. One, how to integrate the expected impacts of energy efficiency into utility resource planning. That's our main focus. And along the way, we're going to be talking about, well, how do you decide how much efficiency is enough? And how do you use potential analyses to set goals and decide what level of funding you might need, that type of thing. So without further ado, I'm going to now mute everybody's phone line, and then we'll take you off later. And we're going to move right into the presentation. So let me... So today's presentation is, as I said, integrating the impact of energy efficiency, both policy and programs, into utility resource planning. We have 3 or 4 objectives for today. The first one is to provide an overview of how energy efficiency resource estimates are actually developed and integrated into resource planning and used to adjust forecasts. We're also going to describe best practices methods for actually incorporating energy savings projections into resource planning and demand forecasting processes, and try to recommend how and where interveners are most likely to be successful in these processes. And finally, stimulate your desire to learn more about this topic if we're successful. This is just a brief summary of our qualification. I've been working in the field of demand forecasting and program savings quantification for over 30 years. Believe it or not, my first job was to develop a worldwide end-use model and then develop high and low forecasts when I worked at the International Institute for Applied Systems Analysis back in 1980. Since then, I've been working on integrating utility program savings as well as standards into CEC forecasts in California, development of the first savings goals in California, and also developed some savings goals for the province of Ontario. And I'm currently working as a senior consultant at ITron. Tom, my partner here, has over 30 years of experience in energy efficiency assessment and integrated resource planning. And he currently is the manager and really the head honcho of conservation resources with the Northwest Power and Conservation Council. Tom has conducted the first and led all the subsequent council assessments of energy efficiency potential. Okay. So we're going to talk about, in this order, methods used to integrate savings forecasts into resource planning models, methods used to develop energy efficiency resource portfolio standards and integrate their impacts into resource planning, and we're going to try to review the strengths and weaknesses of both approaches. Then after that, we're going to talk about the top 10 myths related to electricity resource planning and talk about some examples that we've seen in our work. Give you some suggestions or strategies to improve treatment of energy efficiency resource as a resource in your locale or jurisdiction. And finally, talk about how and where to intervene in utility resource planning processes to ensure integration of energy savings into forecasts, along with the best practices summary. We've also left several slides at the end, probably slides 85 through 110 or something, which gives you a lot of technical appendix information about and additional resources to go to about if you want to learn more about the techniques of integrating energy efficiency into forecasting itself, or just to look at some of the results. So in power planning, there's really only three simple questions that need to be answered. When will we need resources? How much will we need? And what should we build? What type of plant should we build? And when energy efficiency came onto the scene in the early 1980s, late 1970s, they had their own set of questions they thought were important that also need to be answered even before you talk about resource planning. You know, what types of energy efficiency research should be built, procured, or funded? You know, should we focus on peak load or annual energy savings? How much funding might be needed to capture all or most of the cost-effective resource? And how quickly can these programs be ramped up to capture the available cost-effectiveness resources 5 to 10 years out? And that last one is really the subject of a lot of debate these days about how quickly the ramp-ups can happen, and we'll talk about that. So now I'm going to turn the slide presentation over to Tom Eckman, to my partner, and he's going to go through the process of integrating energy efficiency into integrated resource planning at the utilities. So Tom, can you take over? Is there a way to unmute? Tom, are you there? Hello? Guess we're having technical difficulties here. I'm trying to get Tom into the audio portion here. Tom? Can anyone hear me? Hello? Okay, well, I'm trying to reach my partner Tom to take over here. Tom, can you tell me, are you still on the line, or do you want me to just take over for your presentation? Well, I've unmuted the line, and everybody should be able to hear me, but I'm not sure what's happening. Okay, well, I'm just going to assume that I can't reach Tom for a bit, and maybe Robin and Tom can work it out, and I'm going to just go ahead and go through his presentation. Okay, as we all know, it's pretty much a Ouija process to do forecasting of any kind, and here's just an example of a recent forecasting exercise at the Northwest Power Planning Council. So basically, there's two methods to use to answer power planning and e-planning type questions. First one is integrated resource planning. This one started in the 1980s, and basically this suggests that you need to simultaneously compete energy efficiency options and supply options and find out which one is the best fit and which one essentially can provide the lowest cost way to meet the energy service needs of the future in any particular population. And the goal is to try to treat energy efficiency options as equivalent supply-side resources. It's always usually called least cost planning. The other emerging method that's been used to try to answer these questions is just to set energy efficiency resource portfolio standards, and we're going to talk about that as well. In this particular case, a state or a utility can mandate a minimum share of the energy efficiency resources in the utility resource portfolio as a function of percentage of base sales or percentage of incremental growth, or as a minimum investment level. The first focus now is on integrated resource planning. One of the things that's difficult to do is make sure that you have good estimates of cost of both conventional generation capacity, renewable generation, power purchases, any kind of load management programs combined with energy efficiency to meet all the loads in the future. And a good resource plan considers all the necessary features for system operations, such as the diversity of load, reliability for every node in the load, dispatchability, and other risk factors. The overall objective, of course, is to evaluate supply and demand on a consistent and an integrated basis. So there are several basic elements to integrated resource planning. Best practices IRPs are both bottoms up, in other words, starting at the end use level and looking at measure adoption, but they're also sometimes top down. There also usually is a generation resource potential assessment as part of the IRP. And best practices consider uncertainty in both resource costs, construction schedules, and availability. There's a third part of an IRP, which is the load forecast. Often this is conducted independent of the energy efficiency resource potential assessment and the generating resource potential assessment. But the recent trends are to try to include the efficiency resource assessment within the load forecast if possible. And usually there's a range of load growth scenarios modeled between low, medium, and high. And finally, there's some kind of a model that attempts to incorporate and integrate all three of these assessments, both the load forecast assessment about energy service demand, generation, and energy efficiency, into a model that compares different combinations, tries to satisfy a resource selection objective. And there's many different objectives that you can choose. One, minimize net present system value. There's maximizing the value of particular resources, and all within the constraint of meeting some type of system load reliability requirement at some acceptable level of risk. Here's just an illustration of this particular Illustrative Integrated Resource Planning framework. And as you can see on the far left, there's three kinds of input demographics that have to come into the process. You have to do forecast of economic and demographic growth, some kind of forecast of fuel prices, some kind of forecast of energy efficiency available as a function of cost, and a forecast of generating resource and cost. We talked about that before. This feeds into the demand forecast at the top there, which is provides a forecast of total electricity use that has to be met by the resource planning model in the middle there, that yellow box. And then there's that feeds into, that results in electricity price that has to then feed into I'm trying to unmute Tom here at the same time as I'm doing this presentation. Sorry about that. So as you can see, this is all an integrated model, and ultimately you select the level of both energy efficiency resources and generating resources that are considered optimal by the model. So now I'm going to talk a little bit about the analytical process flow. You start with the load forecast model usually, and then that interacts with this energy efficiency resource potential assessment. Then at the bottom, there's usually a potential assessment in terms of the cost of resources and when they might be available and how much for generation. All of these three boxes, the red, the blue, and the orange one, are input into this resource portfolio model. And you need to have a discussion about whether you're going to be assuming frozen or dynamic efficiency levels. And what that means is dynamic efficiency levels is a forecast of the average efficiency changing over time, while frozen just assumes the same level of efficiency in order to be able to count savings. And the load forecast also provides inputs to the energy efficiency resource potential assessment in terms of how much building stock is there and what's the relevant energy service demand that these energy efficiency programs might be able to tap into. Okay. And finally, the generating resource potential assessment provides you with information about the generating resource costs and over time and what it would cost, dollars per kilowatt and dollars per megawatt hour. And the result of this resource planning model is a resource portfolio strategy that gives you option and build schedules, including annual amounts of energy efficiency that would be cost effective to purchase. And now we're going to talk a little bit about some of the definitions that are important in this particular area. First one is, what's an end-use load forecast? It's basically a forecast of demand based on information that's available on end-use and end-user characteristics, such as appliances, customer use, their age, sizes of houses, saturation of different types of appliances at both the household and the commercial level. These models are based on the fundamental principle that demand should be derived not based on sort of projections just straight line from the past, but some kind of understanding of the customer's demand for lighting, cooling, heating, refrigeration, and other energy services. So these models then explain demand as a function of the number of appliances and the level of energy service demanded or work demanded from each appliance system or building. The end-use forecast requires less historical data, but more information about customers and their equipment. They're sensitive to the amount and quality of end-use data available, and often these models are pretty expensive to run. For example, trying to gather information on the distribution of equipment age, like appliances, is important for modeling the energy usage, but it's often a data-intensive exercise. Now, the other main type of forecast is an econometric use load forecast. This estimates future demand based on the relationship between energy consumption and dependent variables and factors influence consumption. And these are usually estimated using some kind of least squares method or a time series regression. So basically, this approach is combining economic theory and statistical techniques for forecasting demand. One of the options in this framework is to aggregate the econometric the consumption into different sectors, and then calculate future demand as a function of weather, economic, and other variables, and then estimate the demand using recent trends and historical data for each of these variables, and usually you normalize the weather. Okay, bear with me, this having trouble switching slides. There we go. Okay, the other term that's going to be important to understand the context of this seminar is end-use econometric load forecast, which is some combination of the end-use model and the econometric load forecast we talked about before. It's basically an estimate of future demand based on direct estimates of energy consumption, which are then linked in combination with drivers, economic drivers such as per capita income, employment in the future, or electricity prices that are often used in econometric models. So this is essentially a way of trying to combine these two concepts into one model. Okay, we talked earlier about frozen versus dynamic baselines. Frozen efficiency baselines are estimates of future loads that assume no improvement in efficiency over time. A lot of analysts like to use this because it lets you come up with an estimate of the total savings that are happening in the marketplace if you define savings as changes in efficiency times the building stock that's demanding that efficiency in a particular year. It does allow for changes in efficiency as a result of normal stock turnover, but it freezes essentially discretionary efficiency for new products, unless there's a change in the code that's part of that forecast. More recently, people have been trying to estimate dynamic efficiency baselines, and that's an estimate of future loads that assumes some kind of baseline improvement in energy efficiency beyond those caused by the normal stock turnover, and that's both codes and standards. And that's basically because there's an assumption that technology improvement trends are going to continue to drive down the prices of some of these more efficient goods, and as a result, efficiencies will change independent of whether or not there's programs in the marketplace. Just to try to assuage my concerns, can someone respond back using the messages to make sure that people are still on the line? So now I'm going to talk about efficiency supply curves. Okay, thanks. If the potential economic energy savings in a supply curve is how much savings is available for a given cost, like cents per kilowatt hour, or a specific point in time. Currently, the best practices are you need to represent achievable potential for retrofits and new construction separately when you're constructing these supply curves. And we use continuous supply curves that look at the amount of conservation that's available at each point, from 1 cent to 2 cents to 3 cents to 4 cents to 5 cents levelized, rather than a whole resource bottle. And then the last thing is that it's important to set limits on annual acquisition levels. In this case, what's the maximum retrofit potential rates? And a lot of utilities have sort of set themselves up for failure by trying to assume that they can ramp up too quickly. For example, spend 50%, reach 10% of the stock this, 20% of the stock next year. You have to be very careful looking at what you can actually do in a particular market and understand that there's lots of constraints to ramping up program spending, by more than 50% a year on an ongoing basis. Okay, so now we're going to talk a little bit about the basic bottoms-up formula for creating an energy efficiency supply curve. We need to try to figure out, for example, achievable potential, and that's the number of applicable units that we decide is achievable or reachable times the kilowatt-hour savings per unit times some estimate market penetration. And usually we get the kilowatt-hour savings per unit numbers by looking at what's currently available and comparing that to the sort of best practices in the market. And current efficiency also needs to be adjusted for adopted codes and standards, as we talked about earlier, as the stock turns over and essentially higher levels of efficiency or lower levels of kilowatt hours per unit are required. And then this is the place where people tend to argue about it is, well, what's realistically achievable over time? And we'll talk a little bit more about that later. So really there's a 6-step process that's usually used for creating energy efficiency supply curves. Step 1, estimate the technical potential on a per application basis. Step 2, estimate economic potential on a per application basis. Estimate the number of applicable or available units. This might be things like households or square foot of commercial area. Estimate a technical potential for all applicable units, which assumes that you could basically pull out, replace everything by waving a magic wand, not worrying about economic constraints. Then you estimate economic potential for all units. And finally, you estimate realizable potential for realistically achievable, and that's where the judgment comes in about how quickly can programs be ramped up. So now we're going to talk a little bit about the definitions of technical, economic, and achievable potential. Technical potential is the total quantity of energy efficiencies available, given commercially available and reliable technology, regardless of cost. Economic potential is, basically what's determined to be cost effective, and that's a function of whatever the avoided cost forecasts are. And you try to essentially levelize the cost of conservation to be less than the current avoided cost or the present value of avoided cost over the applicable time horizon, in this case usually 10 years. And we've talked about this before. Achievable potential is the amount that's found to be realistic for a given time period based on past performance of the programs and policy initiatives in terms of their ramp-up rate. So here's an example of a technical potential assessment for application residential electric water heating. And on the x-axis here is essentially retail cost for these more higher efficient air conditioners. And on the left, the y-axis is the kilowatt hours per year estimated for that electric water heating. And as you can see, this technical assessment suggests that you can go from 3,500 kilowatt hours already all the way down to 1,000, but it costs you a significant amount, up to $1,700 in this particular example. And these green boxes that I'm showing you are just the particular technologies that are descriptions of these yellow points. Wastewater heat recovery, for example, down there at the second to lowest, and then an Energy Star dishwasher with an energy factor of 72. So here's an example of assessing economic potential on a per application basis. Supply curve for water heating. And this shows, for example, that as you increase the energy savings, you're increasing the levelized cost from, something like 20 or 30 mils per kilowatt hour at the start, all the way up to 2,500 mils per kilowatt hour for some of these higher, more expensive technologies. And this, again, shows the points on the curve: the heat pump water heater, clothes washer, Energy Star dishwasher. So these are all different examples of technologies that can reduce the, essentially the demand and therefore the energy use associated with hot water heating in a residential wastewater hot recovery, the dishwasher, and the Energy Stars clothes washer. So this is showing that these essentially are not very cost effective at the end of this red curve here because of the relatively high cost in terms of mils per kilowatt hour, over 300 mils per kilowatt hour, 30 cents a kilowatt hour. Here's an example, I think, from the Northwest Power Planning Council of the steps 3 to 6, estimating both the number of applicable units and technical, economic, and achievable potential. And as you can see, the levelized cost, for these starts out relatively high at minus, these are essentially free measures, minus 327, and has a relatively high BC ratio of 2.7 for the clothes washer. And as you can see, it sort of goes down incrementally to the point where some of these things at the bottom, like the EF72 dishwasher and the wastewater heat recovery, are not cost effective at a 0.7 or 0.6. So here's an example from the 6th Pacific Northwest Power Plan of the estimated levelized costs in dollars per megawatt hour of different types of energy efficiency options. And as you can see, it shows that you've got something like 10,000 gigawatt hours per year that are between $0 and $10 per megawatt hour. And this shows the relative increasing amounts that you can get as you go up the cost curve in these different sectors: the distribution, utility distribution, agriculture, industrial, commercial, and consumer electronics. And as you can see, there seems to be significant potential in agriculture on this particular drawing, increasing over time. So now we're going to talk about, what does it mean to generate a resource supply curve? It's basically just the same thing as the energy efficiency supply curve. How much resources are available at a given cost or at a given point in time. The best practices currently in generating these resource supply curves are trying to get the capital costs estimated as a function of the construction phase, looking at fuel costs, however much the transmission access is going to cost, particularly for renewables if you need to build new transmission lines, and whether there's going to be a need for essentially additional storage because these are intermittent resources, and that's called the system integration cost. Okay. Okay, just trying again to see if we can get Tom Eckman in. It didn't work. So here's an example of the estimated, resource supply curve for the Pacific Northwest. And as you can see, it goes everywhere from geothermal on the far left, which is available at a levelized cost of only $75, I'm guessing, per kilowatt hour year here. And that includes both plant costs, integration, transmission losses, and some estimate of the emission cost in terms of CO2. And so we've got a wide range of resources, everything from geothermal to nuclear to utility photovoltaic on the far right here, which has a cost roughly twice the rest of these resources. Okay, now we're going to talk a little bit about a bottoms-up approach for estimating energy efficiency resource potential in an IRP context. First we need to get some information about measure costs. That's both total cost and incremental measure costs. And we have to go look at both program data, contractor bids, and use retail price surveys. Then we need a lot of information about measure savings. What's the typical load shape that these measure savings are going to be applied to. We also need to know something about measure lifetimes. There's been a lot of studies of the persistence of measures and estimation of survival functions. And we can usually get that also from some manufacturers, and engineering estimates are usually available for the useful life of the product. Hello? Okay, still trying to free up my partner, but no success, so I'll keep on going. You also need to have some kind of a market model that provides the forecast of what's the cost going to be on an hourly basis and under average water conditions, again, for the Northwest. And then, of course, we need some kind of a cost-effectiveness model to take all these inputs from measure cost, measure savings, lifetime, with an estimate of avoided cost to figure out what's cost-effective. And then that all becomes a forecast of the level of savings that's going to be available with respect to the customer's price response, and just the number of eligible units, basically in terms of how much either gas or electricity or what the type of fuel that's being used for any particular end use. And all of that model, that entire bottoms-up model that we just talked about, now has to be input into the resource portfolio model to determine the net present value of different portfolio choices, and essentially to try to optimize the mix of energy efficiency and generation resources.
All callers are unmuted.
Tom, are you on the line?
Mike, can you hear me now?
Yes.
All right.
Why don't you take over?
All right, let's struggle with the final ones then. Thanks a lot. You did pretty well. Okay, Mike left off with the resource portfolio model. We'll just take the next step. The portfolio model has several attributes. It's an economic model, basically, that looks at the costs and benefits and the risk of alternative resource strategies. And the portfolios are really mixes of build schedules in most of the resource portfolio models. It's the timing of when resources get built, the type of resource that's selected, that best satisfies what the objective function of the model is. And in many cases, those are to minimize cost or to minimize cost at a given level of risk. Risk is usually has been a new entrant into most of the IRP planning processes for reasons we'll talk about a little bit later, largely to do with our inability to forecast the future. So I think best practices now are to take into account both the cost of meeting resource needs and the potential risk of doing something wrong that will raise those costs. There are two types of models. I'll call the one type the deterministic model, which assumes that you can optimize a portfolio around a given set of futures or a single set of futures with very limited disturbance in them compared to what you think will unfold. So you have a limited set of fuel prices, a limited set of resource cost and availability assumptions, a limited set of load growth uncertainty. And many of these are what they call linear programs, where you give it an optimization function that says minimize cost, and I know everything that varies, so under exactly these conditions, this is the best portfolio to have. Those are often used for more short-term modeling because the uncertainties are less in the short term than they are in the long term. In the long term, you see models that are what we'll call the stochastic option and build approach, where the model tries to select a portfolio management strategy rather than specific resources to develop after it assesses the cost and risk of various options. So in some cases, it can rely heavily on the market rather than build resources. That presents sort of one sort of risk profile. It can build heavily its own resources and not rely heavily on an open market, and that presents a different sort of resource set of risk and cost. In many cases, multiple scenarios are looked at, which is why we call it a stochastic option. That is, you really don't know how the future is going to unfold. So you test multiple scenarios. A minimum of 3 are typical: the high, medium, and the low. In the Northwest case, we test 750 different futures because we have no idea which one of those is actually going to materialize. So that sort of spans the range of the minimum sort of testing of stochastic options to scenario analysis on steroids. So I want to talk about best practices here. We used the GUMP model in the Northwest, and that's sort of iconic for the futures like a box of chocolates. You really don't know which one you're going to get, and it's important to test lots of chocolates, which is what the Northwest does and what some of the best models around the country do. Inputs to those futures include an estimate of the resource supply curve across all resources. We have assumptions about what the load growth might be, or a range, what the future market prices might be over a range of futures, what future gas prices and future electricity prices might be. Those tend to be correlated with backing up here. So, in our condition, we have a lot of hydro, so the variability of hydro is important. Carbon risk is also important going forward, so rather than pick a particular number for what carbon prices might be, or whether there's a cap and trade, pick a range of those prices and when they might be imposed, range of those costs. Those all go into the portfolio model. The portfolio model chews on those a while and picks arrives at an estimate of what the cost of each of those portfolios might be in a given future, and it varies across future. In high load growth cases, prices go up because we're buying more resources. In low load growth cases, prices probably go down and costs go down because we're not buying much. So there's some relationship to total growth, but there are also relationships that are in terms of the total resource cost that are unrelated to total growth, have to do with market prices or gas prices that might influence the total portfolio cost independent of whether you're growing fast or growing slowly. In our case, in the Northwest, we have what we call an efficient frontier that comes out of the model that basically makes it possible to trade risk against cost. All this is a fairly sophisticated process, and I want to boil it down into one slide because it tends to be a lot simpler than that when you look at it in very basic terms. And when you look at anybody's IRP, the inputs pretty much drive the outputs just like all models. What this particular slide illustrates on the vertical axis is the cost of particular resources in dollars per megawatt hour, and on the horizontal axis is the amount of energy available. We use the term average megawatts, but you can put those in gigawatt hours per year if you want as well. It just, as you go to the right, you have additional resources in your supply curve. As you go up, they cost more. And there are two kinds of things plotted on this graph. One is the average or expected value cost for each of these resource types, and the second is the range of risk associated with those prices where we might actually see higher or lower results because construction lead times get changed, gas prices go up, and as a consequence, combustion turbines or coal cost more, carbon tax might hit, and as a consequence of that, additional resource costs might be imposed because of payment on carbon cost. In the case of renewables, we either have construction cost variance or we get a wind machine located where we thought it was going to be extraordinarily windy, and it turns out not to be the case. We get unlucky. And so what you see in this is if the portfolio optimization objective is to maintain a low-cost future at a low risk, you want to buy resources that are down towards the axis, towards the ordinate, that they're a low cost and they have very low variance around them. And In the case of energy efficiency, its capital cost can vary, but its price is pretty cheap. So all the little green dots there are energy efficiency resource supply, and the blue dots are renewables, and we've got some black triangles there that are coal and a bunch of nuclear clear out at the end, and some renewables that go clear out the end, bearing, the last thing out there I think is central station solar PV, something on the order of $250 a megawatt hour. So the things that vary cause you to want to avoid those kinds of resources because they risk, and the things that are high price you want to avoid because they cost a lot. So in any portfolio analysis model, if these are the inputs, you would expect a lot of energy efficiency to be an output in terms of the strategy and less of the expensive stuff. And if you don't see that result given the supply curve inputs, then something's wrong with the model. So just a short point on integrated resource planning and its influence on transmission and distribution planning. There's a growing emphasis on trying to reduce the use of wire to move things around because it has lots of NIMBY problems and is expensive to locate and build. We need transmission service, we need distribution service to get electricity to people, but in the Northwest and in elsewhere, New York, there's been a serious attempt to use what we call non-wires alternatives to offset the demand growth so that one can defer capital expenditures for distribution upgrades. I'll talk about the Northwest, but it's true elsewhere. Bonneville Power has systematic evaluation of non-wires alternatives to its transmission system upgrades. They've had a couple good successes so far. They were able to lower peak demands by concentrating standard efficiency programs on a little island, Orcas Island out in the San Juans, because there was damage to an underwater cable, and it allowed the expedited development of efficiency resources there, reduce peak demand so that they had time to repair that cable and not have to put in on-site generation, emergency on-site generation that was very expensive in order to meet load growth, meet peak demand. In the early 1990s, this Puget Sound area of Seattle, Bellevue, also experienced a transmission constraint, and as a consequence, the Bonneville Power Administration and the local utilities implemented aggressive energy efficiency programs in certain areas of the Seattle, Bellevue area, Puget Sound area, and they were able to avoid putting in a series of capacitors and transmission upgrades by reducing the peak demand on the transmission system. And this is, I think, other cases around the country. In New York, they've been able to reduce the upgrades to transmission or defer them to local distribution networks as a concept of doing targeted efficiency in locales where there was a hot spot. So Mike did most of it, so I'll summarize it. Thanks, Mike. The principal benefit or the principal focus of an integrated resource planning and how you deal with energy efficiency is it's treated exactly like other resource option. It's consistently treated in terms of cost and risk analysis. The models don't know that it's energy efficiency. They only know its cost, its load shape, and its potential variance in cost and risk and deliverability. So from an analytical standpoint, there's no preference. It's just another input deck to a model that looks like all the other input decks, but it has different cost and risk parameters associated with it. It's not got a green tag. It's just its price and cost. It's important that it compete directly in an IRP sense. Otherwise, we're talking about a different modeling approach. With its KW, its capacity impacts, and its kilowatt-hour impacts, again, cost and risk need to be measured in economic terms of the uncertainty surrounding deliverability and the potential uncertainties about getting either the generating resources online or getting the amount of energy efficiency online on the schedule one anticipates at the cost one anticipates. So, as I say, from an integrated resource planning perspective, the symmetrical treatment of the resource, the direct competition between one set of costs and risk against another set of costs and risk is important and critical to doing it right. It requires, as Mike went through, the development of supply curves and a thorough assessment of resource potential, rather than, in terms of best practices, doing a bottoms-up, where you know how many units at what levels of efficiency can be out there that are potentially amenable to improvement. It requires you have information on the load shapes of the impacts that you're providing with energy efficiency, so you know whether they have what sort of demand effect they have, what sort of a capacity benefit they provide. And that's a fairly detailed piece of analytical work and requires considerable resources to pull off correctly. It also requires, in integrated resource planning, that the load forecast and the supply curve assessment and the development of the integrated resource planning portfolio model itself are tied together so that you eliminate the potential for either under or over counting the benefits of energy efficiency on the load forecast. Many load forecasts have energy efficiency already embedded in them, and if you add to that or subtract from that additional energy efficiency, there's a real potential for double counting the potential benefits of offsetting load growth. So you have to make sure that the load forecast and the supply curve assessment, the energy efficiency assessment, are calibrated to one another. Otherwise, you can get some pretty weird results, saving more than you use being one of those. The principal strength, I think, of an IRP approach is it particularly when it's combined with a bottoms-up assessment, has some real benefits. The first is there's greater transparency because all the assumptions are laid out someplace in a document. You know what the baseline consumption is. You can compare that to metered or billing data to know whether or not those match. You can look at the technology improvement options to see whether or not a full range of technology options from current practice all the way up to emerging technology have been considered, or where they were considered, and what the assumptions were about what their cost and the potential for market achievability or market penetration might be. Those are all made explicit, and that they allow a lot more transparent look at whether all options were considered that look reasonable. If they're done right, there's an internal consistency between the load growth assumptions, so that load growth is not just growing independent of technology. And you note, for example, if TV penetration is going up, that's captured in the load growth, but you also have the number of TVs captured in the supply curve, so the numbers of units that either create load or have resource potential are the same. So that internal consistency makes for the limited opportunity for double counting or undercounting the resource benefits of efficiency. As I said, competing directly with supply-side resources, it's not an afterthought or a second imposed from outside sort of guesstimate about what the impact of energy efficiency might be. It's a direct competition, economic basis, and risk basis. A secondary benefit, but not small, is that it provides energy efficiency program planners a lot of information on which to base program designs. Because you have the resource identified by market, you know where the measures are, which ones represent major potential, which ones don't, which ones are less expensive, which ones are more expensive, and that can help drive your budget, because if you know these are expensive measures, you need more money to acquire them. And finally, we'll look at some of the weaknesses. I think the biggest weakness is it takes a lot of resources to do this correctly. You can't underestimate the amount of detailed information, data required in order to do the bottoms-up and the high-level analysis on resources. And it takes time to do that on the order of typical integrated resource planning cycles are between 18 months and 2 years, and the first year and a half of that is really data development. There are not many resource portfolio models out there that do direct comparisons of, so you can't really buy one off the shelf. Many of the resource portfolio models take a load forecast that embeds in it energy efficiency as a exogenous variable and reduces the load by some presumption about energy efficiency, and then it determines what other resources are needed after the load forecast has been reduced. And that isn't a direct comparison in an integrated resource planning process where both generating resources and energy efficiency come in the form of supply curves, and the model determines which supply curve to purchase from first. There's also a real potential to get false sense of precision out of resource planning, particularly those that look at a deterministic future, and we'll talk about the limits of that in a few minutes. But one has to be really careful that the plans on which you base, or the portfolio on which you base your resource choices can withstand a robust set of different futures than you expect. And so if you assume in the long run that you're going to have a certain level of load forecast and you don't get it, you can easily buy too many resources and overbuild. If you assume load growth is offset significantly by energy efficiency and you don't buy enough, you can find yourself in a shortfall. And you don't want to assume that you know the future particularly well because the level of precision you can get out of the model isn't anywhere close to the level of precision you can forecast the future for. There are some limitations in models in terms of EE resource development that really can't handle some of the resource needs that some of the power system needs, like dispatchability and load support, K-bar support, and other things that are power system operations requirements. And the ability of energy efficiency to meet all those needs is limited. It can provide capacity offsets, but it's not the same as it can reduce peak demand growth, but demand response resources are better suited to reducing system peaks for reliability reasons, and energy efficiency can defer load growth, but it can't meet reliability problems if you lose a transmission line and you need system support to have redundancy in the transmission system to avoid the problems created by that. So it isn't a panacea to solve all power system needs for new resources. There are sometimes needs for support independent of the need for new generation. Let's see, I just talked about this. While we got peak load reductions because of reducing energy consumption, peak loads are also going to go down. It often doesn't drive what resource expansion looks like peak-constrained utilities because the peaks typically grow faster than the average. And energy efficiency, while it can be offset peak, doesn't offset as much peak as demand response resources. For those people who are trying to integrate wind, it can't provide within our load balancing. It just doesn't follow load that fast, and you can't ramp it up and ramp it down. It's not dispatchable in any way, shape. The IRP process, I'd be remiss if I didn't point out that in many cases the processes can be pretty adversarial and political, and the answer doesn't necessarily come from the model. So these are public involvement processes by and large at some point, stakeholder engagement processes, and the models don't provide the answer because they're not all the boundary conditions under which decisions get made. So one has to be careful while pointing to the model output as useful information for decision makers. It doesn't print an answer for you. There are a lot of assumptions that go into these models about the future and about cost, and those can be tuned to the local politics pretty easily. And so one has to, it provides, because of the transparency, there's real benefit there, but they're also subject to manipulation like any other future. Mike, I think we're coming back to you here.
Yeah. So now, thanks everybody for putting up with our fumble on the unmute and mute of phones. I'm glad that Tom got to finish off. What I'd like to ask now, before we get into the second method of identifying the optimum level of energy efficiency resources that one might want to go into, are there any questions for Tom about the slides that were just presented in terms of his opinions of different IRP processes, or just any questions that you might have? You can either type the questions in and I'll see them and we can both see them, or you can just type up right now orally on the phone. So first off, can someone just out there confirm that they're able to talk so we can listen to you?
Can you hear me? Some of us can.
Hello. Okay. So we have two questions, Tom. The first one is, how big of a problem is it if a resource plan is developed with energy efficiency model as an input to the resource plan, but then modifying the load forecast, but then multiple EE scenario inputs are offered later to the modeling group?
I think, by and large,
This line is now
any resource portfolio modeling process should be able to take multiple scenarios for resource availability, whether it's generating resources or energy efficiency. If the model can't do that, it's pretty limited in its scope, because you need to test varying levels. For example, the Northwest tests varying levels of ramp rate for the ability to achieve ramp up energy efficiency over time. And so in some cases we constrain that, saying the infrastructure just can't build energy efficiency any faster than that, or we take the lid off and see how fast we could push it. And so you need to be able to see what the benefits and costs of alternative scenarios are. So the load forecasting model can also be used to do the same thing. You just temper or increase the rate of load growth, and that difference is caused by ramping in energy efficiency at different paces or with different levels of success. And I think it shouldn't be a problem, and you certainly want to test multiple scenarios of that to see what the cost and risk associated with going faster or slower or achieving more or less than you'd anticipated are.
Okay. And I think we have another question that kind of builds off of that first question. And the question is, where do you incorporate sort of probability assessment into the risk analysis? And have you ever seen an IRP process that essentially puts in inputs but then has a probability associated with that input being the actual value?
Yes. I think there are many cases. The Northwest model that we use is a Monte Carlo simulation, and each of the major inputs, gas price forecast, demand growth levels, are input as probability distributions, and they're combined into future. So we have declined from trying to identify what they call a mean reverting future. That is, we have expected values in each of the distributions. We have a range, and the probability distributions. I think we've decided that we're humble enough not to know what we expect the future to be, only what we hope it might be, but we're not trying to identify a specific value. There are many cases where you see resource portfolio models that have a high, low, and reference case, which is their expected case. And the problem we see with that is that you rarely get what you expect. And so you really need to test the range of outcomes to see what's raising the risk of a particular portfolio and what's making it work really well, so you can adjust your portfolio modeling, portfolio strategy based on a range of outcomes rather than a predestined future. That's pretty hard to optimize about the future when you don't know what's going to be. So you may want to temper the range a bit by what you think future natural gas prices might be, but we're testing a pretty wide range, and there's not really an expected value or normal, an average case or a reference case.
Right.
I don't believe it.
And Tom, let me just build off of that slightly. I'm also aware of processes in California and other states where people are now modeling energy savings as a probability range, the forecast of likely savings, because in many cases people have gone in assuming that they're going to get gross savings of X for any particular program, and it turns out that over time those gross savings have deteriorated because of advances in measurement techniques and people switching to net savings in the middle of the process. So it's important to understand that energy savings projections are also uncertain, and you can handle those within a Monte Carlo framework.
Yeah, we have energy efficiency uncertainty as a variable in the model, so it's a distribution as well. Just like any other resource, it has some likelihood of achieving more or less or costing more or less than you anticipated.
Right. Okay, any other questions before we go on to the sort of second method of determining energy efficiency over time? Okay, hearing none, I'm going to jump in, and then I'll be talking for 20 or 30 slides here. We'll have another question period. And like I said before, feel free to type in any questions that you have during this presentation so Tom can cue me in on whether I need to go back or answer any questions as I move forward. Okay, so we talked about integrated resource planning already. Now we're going to move on to the second level, the energy efficiency resource portfolio standards, which is, now there's these types of standards in over 24 states. And some people think that they've gone to this more direct method of trying to figure out how much energy efficiency should be procured in the state because of uncertainty about whether the IRP process was going to work well or just the overall cost. There's been many IRP processes that were stopped either because of deregulation or the cost of feeding the models. So this is essentially a simplified process of trying to estimate the impacts of efficiency over time, and it has both strengths and weaknesses, as we'll find out as we go deeper. Okay, so what are the basic analytical elements in this approach? First of all, you still need an energy efficiency resource potential assessment, same as the IRP. But you don't need a generating resource potential assessment. Instead, all you need is a range of avoided cost forecasts that represent the sum of what people think is available on the margin in terms of generation supply or transmission upgrades. And the best practices consider sort of uncertainties in these resource cost forecasts, construction schedules, and availability. So that represents a significant savings because often there's a lot of cost that is necessary to incur to do a generation resource potential assessment, but it's easier to find this avoided cost forecast. The load forecast basically still has to be done to set the baseline sales metric, and it's basically the same in IRP as it is in the Energy Resource Portfolio Standard approach. And now let's see if there's anything else different. Now, this is the other potential savings, is there's no resource portfolio model needed. The policy is just usually set on an analytical basis or some type of regulatory judgment. And there's a supply curve analysis used to define some minimum level of savings goals that are achievable over time. And the best practices sort of vary by choice of method. I would say the jury is still out about whether IRP or Energy Resource Portfolio Standard produces the best public policy outcome. One is, it sort of makes the assumption that energy efficiency should be the first resource procured, and then goes from there up to the limit of the supply options, where the IRP has the benefit of dynamically looking at different combinations of energy efficiency and generation, and presumably if given ideal inputs and enough time, would produce a better result. But as I've been saying, some people are going for this sort of second best method because they think it's the best way of jump-starting energy efficiency in their particular area. So there, as I said before, there's a range of energy resource portfolio standards that have been mandated in North America. One of the key things is to look at whether these savings goals that are mandated are expressed as a percentage of annual sales in the baseline forecast, or a percentage of incremental load growth, or more recently, people have been looking at percentage reductions in per capita consumption of electricity, for example, in Maryland. These portfolio standards are complicated by the fact that often there's rate impact or program spending caps set by the legislature or the regulatory authority. So you may have a really high goal, and if you've got a program spending cap, you may not be able to get there, or some rate impact cap. And we've seen that in some cases, program spending caps results that utilities have to stop the program, in the middle of the year or in fall because they've run out of money. And then finally, I'd say, setting the actual goals itself are usually associated with some type of energy efficiency potential study. ITron was involved in doing this in California and Texas, but there's many other examples as well. And we think this is kind of a best practice to try to make sure you've done some type of potential analysis before you go to the legislature and set minimum performance standards. So moving on. Okay, so basically, as I mentioned before, there's two methods to develop these energy resource portfolio standards. One is an analytical approach that starts with potential analyses, and you attempt to define achievable savings metrics over a fixed time period. It can be either done with forecasting models or it can be done exogenous to forecasting models. You also need within your potential analysis some model that can try to estimate likely customer adoption behavior as a function of either price or information or other types of customer operating variables. And you also need to limit the feasible sort of ramp-up rates in terms of savings based on historical practice in your particular jurisdiction. And then the other thing that you need to do that people often don't do is look at a forecast of incremental measure costs. Are you going to assume that those stay constant over the next 10 or 15 years, or should they ramp down or should they ramp up? Most people tend to assume that they're just constant. And that works for some measures like insulation, but it is definitely wrong for other measures. For example, CFLs, the prices dropped from $14 a bulb in 1980 to $250 a bulb now. So if you would have forecast constant prices, you would have been wrong. The other big choice that you have to make is, what do you want to include in your resource potential standard? Do you want to include programs only, utility programs only, or utility programs plus some assumed implementation of building and appliance standards over time? And I'm aware in some states that they've done programs plus standards, but most states choose just to do utility programs currently. Of course, the other possibility in terms of setting ERPS is just a political, lobbying effort only. There's many places where this has been done in Massachusetts, Maryland, Pennsylvania, Ohio, where a group of advocates went in and said, we think this is the right metric, 2% or 1% of sales over time, and it was sort of, those values were negotiated in a legislative process. And as I said before, the risk of that is that in a political process, since it's management by committee in some cases, you might build internally inconsistent constraints into the legislation, like low funding caps coupled with high savings goals. And that has led to paralysis in some states. Okay, at this point in time, I'd like to get some feedback from the audience. If you could just type in which method, analytical or political, is used to set goals in your jurisdiction or state, and which methods do you prefer and why. And we'll keep your responses anonymous, but I'd like you to just think about, if you're in a jurisdiction where they've set resource portfolio standards, would you characterize it as an analytical process or a political process? And state your opinion in terms of which method is best and why, if you want to. Okay. Someone should turn off that noise in the background. So just so everybody knows, I have a range of responses, everything from Political was analysis to justify it, to analysis primarily. So we'll just move on. So as I mentioned before, there's a big question that one needs to answer when you set the ERPS goal. You want to set it on total market gross savings potential, which is the sum of all savings that could be achieved by both programs or policy initiatives or standards or labels. And that's the approach that's been taken in California and New York. Or do you want to limit it solely to the net savings achievable, net savings attributable to a specific set of programs? And examples of that are in Ohio, Maryland, and Pennsylvania. They've said, we need to make sure that these are savings that are measured and only attributable to the program. Okay, next slide. Okay, we've already given you the definitions of technical, economic, potential, and achievable in a previous slide, but I added one here because I think it's really important for everyone to think about, and that is implicit in most forecasts of electricity demand and natural gas demand for that matter, there is an estimate of naturally occurring savings, reductions in the average UEC for a given end use or for a given sector that's driven by technology change and customer adoption. And we tell people it's really important before you come up with your estimate of achievable potential that you figure out, with respect to the baseline or dominant forecast in your region, what are you including in achievable that's already naturally occurring? And if you don't do that, the problem becomes your utilities may have achieved, report achievable savings that are exactly on goal, but the evaluators come back and ding them and say, yeah, but 20% of that was naturally occurring anyway, so you can only get credit for 80% of that. So that's why it's really important to talk about whether or not your ERPS includes naturally occurring savings or not. So this is another important issue with respect to energy resource portfolio standards. You need to know when people are adjusting forecasts, are they adjusting it based on gross energy savings from the program or net? And for example, in the Northwest, they focus mainly on gross savings, but in many other utility areas, they focus on net savings. And it's a real problem if you've done your potential analysis from the perspective of growth, and you try to integrate that with a forecast that's working on net, or vice versa. So it's important to specify, if you can, whether these savings are gross or net when you set the energy resource portfolio standard. Okay, here's just a flow chart of what kinds of data are needed to do an energy resource portfolio standard in terms of both the potential analysis and then later setting the goals. And as you can see, most of this information is similar to what we needed in the IRP process. We need forecasts of costs, rates, what types of programs are available, their funding level, whether incentives are capped or not, and whether, what kinds of incentives they're going to offer as a function of incremental costs. You need a lot of information about customers in terms of total number in the segment, load profiles and usage profiles, and some kind of model that says we expect X fraction, 20% of the customers to adopt investments that have a 2-year payback or less, or a 5-year payback or less. So in addition to the customer data on the right-hand side, you need technology data, which includes specific technology definitions for each of the end uses, what level of efficiency you want to include as available and at what cost, as well as information on fuel share. And you put this all into sort of a technology adoption data model, and it yields information about adoption results, net savings or energy impacts, impacts on the utility, and then good models come out with benefit cost results depending on what perspective you want. So that's just an overview of what's in a typical model that looks at potential and then turns that into a goal level over time. 17. Okay, here's just a graphical representation of technical, economic, achievable. You can see that it keeps shrinking over time. And at the very center of this core is what I talked about before, is some estimate of naturally occurring savings, and you need to make sure that you know what that is both in the forecast model and energy efficiency model, which is used to assess what level of savings might occur over a 10-year time period. Okay, so what are some of the key uncertainties in these potential studies? Well, I've listed 4 here. You know, the forecast of measure adoptions is highly uncertain, primarily because people aren't willing to spend the money to go out and do sort of experiments to figure out people's revealed preferences in terms of what fraction of the population will adopt a measure that costs $50 now, but saves $250 over the life cycle, for example. And is it best to estimate or model adoptions as a function of simple payback, or simple payback plus some information exposure variable, or there's a variety of other variables that are used in measure adoptions. The second key uncertainty that often I don't see documented is what's the forecast of incremental cost over time. Usually it's held constant in real terms, but as I suggested, for some measures that turns out to be incorrect. Some measures, their real cost is falling over time. That's certainly true for things like refrigerators and more efficient water heaters and certainly more efficient lighting. But I would again suggest there's a lack of empirical data on the cost of incremental measures over time, and that might be something you would consider doing in your particular area so that you could get more accurate results about what might be cost effective. The third point here I want to really emphasize that the results are dependent on, all kinds of savings results are dependent on the forecasted level of energy service demand. When you have a recession, for example, and you forecast lower energy service demand, that by definition reduces the amount of achievable potential from savings. And what I don't think a lot of people recognize is that setting those goals, you need to make sure you understand, is there a baseline forecast of energy service demand that everybody in the jurisdiction or state accepts? And what happens if we enter a recession? Are you going to automatically adjust your energy resource portfolio standards goals to take into account that lower service demand or not? And that's an issue in many states now where it looks like it's going to be, quote, easy to achieve their savings goals in some cases because of the recession, or in other cases, because of the recession, it's going to be harder because they've set the goal in terms of per capita consumption or other kinds of variables where the drop in consumption makes it harder to get to the absolute savings goals that were set in the earlier legislative process. And then finally, you need to be very careful to understand what's the definition of achievable. Is there a specific customer adoption model that was used to define achievable, or was it more a study of how have the utility programs performed over the last 10 years, and what level of increment were they able to support over time as a function of either funding or just regulatory practice? Okay, so the next, I'm going to talk a little bit, well, how would we describe these analytical processes used to determine savings goals? Is it really precise targeting where you get to an exact result? And if you look at most of the energy resource portfolio standards, they assume that there is an absolute fixed amount that you have to reach, like what percent of sales or 1,000 gigawatt hours in a particular year. And we would argue that there's an uncertainty bound or range around that, and it might be more precise to say the goal is 1% plus or minus 10%, because we don't think you can measure savings at the accurate level that's required in some of these statutes, or at the precision level that's required in these statutes. So what steps are used in the analytical process to derive portfolio standards? Usually there's a resource potential analysis. There's a discussion within a public forum of the economic, infrastructure, and policy constraints to actually achieve and develop savings goals over time. There is an attempt to take whatever has been developed in terms of an energy saving goal and try to integrate them into the load forecast. and decide what your goal setting philosophy is. Are you setting aspirational goals, which you think there's a 50% chance of not achieving, or are these goals 90% certain that they're going to be achieved? And that's important in terms of looking at the probability. And then you need to include some kind of a process to modify the savings goals, because the savings forecast is almost always wrong the first time out. That's what I think we've learned through at least 20 years of experience. And I'm worried that a lot of the energy resource portfolio standards that have been set have no such process to modify the goals. They just set the goals and say, this is going to be it from now until 10 years from now, and that leads to heartache usually at the end of the process. Moving on. So we've talked a little bit already about the efficiency resource potential analysis. Here are the key assumptions that need to be made: incremental efficiency costs, efficiency, the level of energy service demand, what you think customer adoption behavior is going to look like, whether a particular program is likely to mitigate known market barriers or not, and whether you have a good idea of all the available program delivery mechanisms. And all of these are assumptions that the modelers have to make in order to give you a good savings potential forecast. And here's an example of adoption rates that are affected by the severity of the market barriers. And as you can see, this is an actual result from an ITron potential study where if our information from the market research suggests there are no market barriers, which is rare but sometimes the case, then we have 50% of the population adopting it at a payback of 2 years or less. But if there's extremely high market barriers, then you may not get to that same level until you get a benefit cost ratio of 15 to 1, which is what's shown on the x-axis there. So this is again just the results of attempting to quantify known information about market barriers and to characterize them as either low, medium, or high. And since your model can calculate benefit cost ratios for any particular measure in any different segment, this gives you a way of translating what fraction of the customers are likely to adopt given the information that you have about payback and barriers. Okay, here is an example of an analysis where you try to estimate the savings potential from both programs and state standards and federal standards and a set of big and bold policy initiatives in California. And the reason I'm doing this, showing you this example, is first I want to make sure it's really important to show what his history has been like, both in the short term and try to understand what you really know well for the next 3 years. And then the uncertainties become a lot larger when you go into this sort of uncommitted program period from 2012 to 2020. And as you can see, the IOU programs become a much more significant part of the total savings by 2020, in part because there's an assumption that the funding levels are relatively certain in this analysis, and that the PUC is likely to continue to support that. And also illustrated here is the effect of, for example, the Huffman bill is a requirement to phase out of incandescence in California by 2014. And you can also see the impact in green here of Title 24 and federal standards becoming a more significant portion of savings as time goes on. So it's impossible essentially here to look at the components of the total market forecast of savings in terms of both programs and price effects and the impacts of existing programs. Now moving on to the next slide, if I can get the. So here's an example of why it's really important to talk about what are the underlying assumptions in an energy resource portfolio standard. And we show here, this is an example from Texas of if you assume that CFLs are going to be essentially required by 2014 by federal standards, and or you think they're going to become, essentially market-driven and people are going to buy them on their own without any programs post-2014, you get a much different estimate of the available savings in, over a 10-year period. And you can see in the pie chart on the left that lighting savings are forecast to be 43% of the total savings when you include CFLs. And if you take CFLs out, lighting goes down to 4% of savings. And so, the assumption you make about naturally occurring savings here has a big significant effect on how much savings is available. And, again, with CFLs, there's 3,375 gigawatt hours available. In this case, I think it was in 2015. And without CFLs, it drops by a factor of 3, essentially to 1,350 gigawatt hours. Okay, this is just a discussion again of this step 2 in the Energy Resource Portfolio Standards, looking at the constraints, both funding, infrastructure, and personnel constraints for the people who are developing or delivering the program. It's always important to look at is the utility management likely to be motivated to pursue EE, or are there financial constraints? And then you need to look at trends in customer awareness of programs. What we find when we typically go into a new jurisdiction is the biggest problem that utilities face is that most people are not aware that they have programs, much less, making decisions about what types of energy efficiency to develop in. So we always try to model, customer awareness as a function of how much utilities and the state energy agency, for that matter, are spending on to try and increase awareness of energy efficiency, both program opportunities and technologies in general. It's also important to understand trade ally awareness, whether they're going to be moving towards working with utilities and programs, and whether or not they perceive energy efficiency products to be profitable in their business. And we also ask questions about, do you like working with utility program administrators? That's also an important thing to look at in terms of the likely savings potential. Okay, I'm going to pause here for just a second. Tom, are there any questions that you think I should answer now before I move on to step 3?
None have come in right now so far.
Okay. Oh, I have a question note here that Laura Atkinson said that she's absolutely right. The federal standards for lighting do not actually ban incandescence. They set a much higher efficacy level. Some people in their forecasting shorthand have assumed that the result of those standards will be a big increase in CFLs available. Other people disagree and say that there's going to be modifications to existing incandescent lamps that will be able to meet the standard. And you're right, nobody really knows the answer to that question. It's something that has to be treated as an uncertainty variable in your analysis. Okay. So I also have a question from Meredith Wingate about, well, how do we know what level of market barriers to apply, high, medium, or low? And is it measure specific or jurisdiction specific? Well, the way that we know the answer to that question is we usually do primary data collection of both residential customers and commercial customers, and in some cases industrial. And we ask them about known barriers and whether they see those barriers as significant in making their energy efficiency investment decisions. And we have a way of quantifying if we get so many answers about barriers, then it becomes high. If there's like 8 barriers, it's high, 4 barriers, it's medium, and 3 barriers, it's low. And the other question she asked is it jurisdiction specific? And the answer is yes. We see in some jurisdictions the barriers related to awareness are really high, and in other cases the barriers related to awareness are really low. And similarly for sort of tenant-landlord split barriers, they're very significant in some areas and in specific market segments and not in others. So we need to make an assessment of the type of barriers and the extent of the barriers on a case-by-case basis. Okay, so now I'm going to move on. I answered those two questions. This next thing is about, well, how do you integrate the savings forecast into a load forecast? You know, if you have a forecast of 1% of annual load growth, couldn't you just take 1% off the top and you'll be fine? And it turns out the answer is not that simple. You need to try to determine the embedded savings in a baseline forecast and compare that to the level of savings you found in your EE goals assessment. And then the other thing you need to do, which I mentioned before, is make sure that the underlying forecast of both population and household formation and sales in the commercial sector are compatible between these two models. There's many cases where the EE potential assessment, you know, uses some rosy forecast of household growth at 2% per year or income growth at 2.1% per year, and a different assessment has been used in the underlying forecast, and that makes it so you're comparing apples and oranges, and you have to spend some time adjusting the savings levels to make sure that they're compatible and you have basic drivers of structural demand are the same in the energy forecast as well as in the goals assessment. The third step here is you need to use some kind of expected value analysis to determine achievable savings, not just your most optimistic scenario, but as Tom said, use a Monte Carlo simulation of what might happen. And then I think this is the most important one that doesn't necessarily get put down on paper, but people should know, and all of the parties in a state should know, is what was the goals philosophy that was used to set this standard? Was it a stretch goal where there's only a 10% chance that this goal is going to be achieved? Was it an aggressive goal where there might be a 30% chance? Or is it a predictable goal? I've heard some jurisdictions say it's predictable. We think there's a 50% chance this goal will be achieved. Or, you know, really was it ensure early victories? We set the bar high in the early, 2012, 2015, because we want to make sure that we can point to some successes and not overstress essentially new program administrators by setting up some daunting goal of 1% or 2% of sales. And reference 2, in the references slide at the end of this, goes into more discussion of both goals philosophy and the gross or net savings in the forecast. Moving on to the next slide. Okay, this is an important step that often doesn't get taken in many jurisdictions is, okay, now that we have set some goals, how do we integrate the verified or evaluated program savings into the modified forecasts or goals going forward? I think an important question to ask is how often should energy resource portfolio standards be modified based on program or portfolio evaluations? Should it be once every 5 years, once every 2 years, once every 10 years? And it's also important to think about, well, what might the unintended consequences of setting aggressive goals might be? You know, if the utilities are motivating people to work with them and it's all based on some perception that they're going to meet the goals and then they don't meet the goals, how will that sort of repercussions of that filter out to the various people who are working with them, trade allies, their EM&V consultants, et cetera? And then I guess the final thing is we think it's really important to make sure that you go back and calibrate the forecasting model with the reported or verified program results and the impacts of adopted standards to see if your model can actually backcast accurately what the sales level would be given the level of savings that have been assumed in the forecast. Okay. So in terms of the frequency of energy efficiency resource updates, we think best practices are probably revising the forecast every 2 years based on the verified program savings that have been observed. And opinions vary, but updating a resource potential analysis probably needs to happen once every 3 to 5 years. We've seen people stretch it to 10 years and with some bad results, so we recommend 3 to 5. And we would also say that you should suggest some kind of goals, RPS revisions, at least once every 5 years. Okay, so what kinds of savings metrics have actually been adopted so far? These slides are just going to go through essentially what has been said in various states. Interestingly to me, the vast majority of the ERPSs have been set as a percentage of current year sales, about 87.5% of the states that we're we're familiar with. Only 4% use it as a percentage of load growth and 4% as a percentage of prior year sales. And there's one state that I know of, Maryland, that uses reduction in per capita energy consumption. Okay, so we're going to just show you essentially the results of this savings metrics in the next three models. The record of meeting goals actually is mixed, and it's a function of the savings goal philosophy. Aggressive goals, at least in our opinion, have not yet been achieved where you show net savings that actually is equivalent to 2% above annual sales. We know that in Vermont, there's an estimate of gross savings that got there, but we haven't really been able to spend enough time. I think the claim is that in Vermont, it's 2.4% of sales was achieved in 2008. Okay, I'm not going to read through each of these. You can go through them at your leisure. This whole presentation will be available on the WRAP website afterwards. But this just gives you a state-by-state readout of what annual, program savings or total market savings have been set as a percentage of electricity sales, and the estimate of cumulative savings as a percent of forecasted sales by 2000 and X. And I said XX because it varies by state, whether they set the goal for 2030 or 2025 or 2010. There's a lot of different legislation out there. I think what you can see pretty consistently is that there's usually a near-term goal set and a long-term goal. And there's not yet consensus about whether some of these goals have been met yet or not. It's still being debated in California, for example, whether the goal was met in 2008. And one of the things that we're trying to track, and we will continue to provide updates to people on this call, is what percentage of the states where they set goals have the utilities actually met the goals? Okay, here's another review of sales goals that have been set in Vermont, Massachusetts, et cetera. And you can see how they all vary, but they seem to range between 1% and 2% of sales by utility. And they usually have fairly aggressive numbers out here towards the end of the period of between 11 and 5 and 20% of sales by 2020. And here's the last set of states that have it, and as you can see, there's 3 states that we're aware of that still have pending goals. In many cases, some of these states have said, do all cost-effective energy efficiency, and they haven't yet turned that into a specific energy resource portfolio standard level in a particular year. And my understanding is it's still pending in Wisconsin, and it's still pending in Utah. So we spent some time going through this whole energy portfolio resource savings approach. What are the strengths and what are the weaknesses? Well, from my perspective, it's really important to establish a funding floor for certain kinds of energy efficiency investments, either at the program level or by customers, and it provides more certainty for this sort of energy efficiency professionals to grow over time. So that's a plus. It usually provides a stable base of funding, but in some cases that hasn't proved to be the case. The funding was thought to be stable, and people came back in and raided the funding for other budget woes. In my view, and Tom and I might slightly differ on this, it reduces the cost and time needed to arrive at an answer. Some of these IRP processes are drawn out and can last 6 to 12 months. This process basically reduces that time to a legislative process of 6 to 12 months of lobbying, and then there's an answer available for the next 5 years that utility program planners can support and know as the baseline for doing their planning. The other advantage I would think is that the energy efficiency advocates don't need to rely on the results of essentially a political resource planning process where the choice of the right mix of supply might be heavily influenced by lobbyists and various other parties that come in. And I would say that these energy resource portfolio approach is more likely to be a barometer of the impacts of EE on the financial health of the utilities and less of a sort of political contest about whether nuclear, coal, or natural gas or energy efficiency is the resource of choice in the future. However, there's also many weaknesses to this approach, which I'm going to get to just a second here. One of the primary weaknesses is that you have to assume a ramp-up rate to reach the savings goals, and there's often not a lot of analysis of what are the critical factors to allow a utility to, for example, increase their savings from 5 megawatts in year X to 10 megawatts in the next year to 15 megawatts in the next year, if that's a particular metric. We find that many states, for example, have adopted these goals without looking at, are the utilities going to be motivated to pursue energy efficiency? Will it be profitable to them? Is there an infrastructure of trade allies available to help this ramp up? And how long do we need to invest in that infrastructure before you can achieve these rapid ramp up rates? And again, as I mentioned before, what's the customer awareness of program availability? The next weakness that I would point out is that people often set goals on a gross basis. The savings get evaluated on a net basis from programs, and it leads to a disconnect and controversy. And California is sort of the poster child of controversies about differences between goals set on a gross basis and evaluated on a net basis. And they still haven't reached convergence on what the actual savings are in California. I would say, based on my review of about 30 different jurisdictions, that growth rates and annual savings of greater than 30% per year are often implicit in some of these goals, but they're difficult, if not impossible, to achieve. And the reason is that for some utilities, it's just really hard to, even though you have all the money in the world, to hire the people that you need to roll out the programs, to work with the trade allies. It's very difficult to sustain, a situation where you're starting with, let's say, $5 million a year in year one, and then you ramp up to $8 million in year two, and then you ramp up to $12 million in year three. If you have that dramatic growth, it's difficult to manage that and sustain levels of annual incremental savings of more than 30% per year. And I'm not aware of any utility that's done that. What you tend to see instead is you see these roller coasters where there's a big increase in funding and increase in savings for 2 or 3 years, and then there's a drop-off for 2 or 3 years as the system consolidates, and then another big shot up in savings and funding to the next level. So, one of the things I would hope is that we would try to get to a more sustainable ramp-up rate rather than assuming, sort of boom and bust over a 5-year periodicity or cycle. And then the last thing I'd say is, ERPS has lower credibility with supply-side planners. They just think it's some fantasy dreamed up by energy efficiency advocates in many cases. And there's not very clear consequences of failing to meet savings goals in many cases. Some cases it's just try your best. In other cases there's penalties. In other cases there's just sort of public disapproval, but no real teeth if you don't meet the particular savings goal. The benefits, I would say, of using this type of potential analysis are manifest usually to all the stakeholders, and they're in the form of, there's lots of information about cost effectiveness that you can take from these studies in the form of supply curves, and it highlights the need for people in the program level as well as the load forecasters to understand naturally occurring trends in energy efficiency investment. As I mentioned before, you don't need detailed information on the characteristics of existing or future supply options. You just need an avoided cost forecast. So, Tom, I want to ask you, how are we doing for time?
I think you're on the line.
Does that mean I need to speed up, or we're okay?
I think we're right okay.
Okay, great. So the last set of weaknesses that I want to mention in terms of potential analysis to support energy portfolio resource standards, the linkage and consistency of inputs used to drive econometric forecasts of sales is rarely analyzed. Often they use different inputs. We spent 12 months trying to potential studies with load forecasts, and it's often extremely data intensive and costly. So that's the basic weakness of this approach, is that you're not necessarily integrating the efficiency directly into the load impact forecast. It's usually a 2-step process: do the forecast and then try to put the energy efficiency in. That can be very costly. Of course, the second thing is updating these potential models can be very expensive and data intensive if it's carried out at the measure level. And we're working on various things at the top down. There's no need to incur lots of expense in collecting primary data. And the final weakness is that models aren't very good in assessing the relative cost and risk of the timing of energy efficiency additions. You know, is it important to have steady growth over time, or do you need to ramp up quickly and then actually drop down for 2 years based on the particular resource supply in your service territory or not? These models can't really handle that question. Final set of weaknesses. Don't directly test the cost effectiveness limit for energy efficiency resource development in an ERPS approach. The load reduction targets that are set in the political process may not be tied explicitly to measures and may be viewed as arbitrary. And often net to gross ratios associated with programs change over time and thus reduce the level of verified or evaluated savings. And so it often triggers the need to readjust goals based on evaluation results, as we had mentioned before. Okay, so now given these pros and cons of an energy resource portfolio standard, please send your comments to the following question. Does it make more sense to assess and procure EE savings within a resource planning process context that Tom and I discussed? Or do you think it's better to do it in an independent process that focuses only on potential and costs of various kinds of energy efficiency programs and resources? Please be ready to support your vote with a rationale, and we'll just go through these savings. At the end of the discussion, we will go through your votes and talk about what it means in terms of the pros and cons. Now I think I'm ready. I think we're ready to turn it back over to Tom.
Mike, there were a couple questions. One on whether Michigan should be. I think Marty Kushner said Michigan's standard was 1% annual savings by 2012. It wasn't the 1% cumulative on your chart.
Okay. And
Massachusetts is going to 22% rather than, I think you had NA, didn't have that quite yet on there. So 22% by 2020.
Okay. Yeah, I have no reason to believe that those two corrections are not correct. I will go back and check it and send a note out to the people. But as far as I know, the last time I checked in Massachusetts, they were not so sure that they could get to 22% by 2020. I don't think it was in the legislation. So I will go back and look at that. Okay. Tom, I want you to take over now and give us the top 10 myths in resource planning.
All right, we'll do that. Mike and I have been involved in this over 60 years between us, and we put together a list of our top 10 here of the myths that are used in resource planning and a little bit of debunking, we hope, of those myths, so that if you perceive that you're being told a myth, you'll know what to say about it. Mike, you want to move it forward on my, there we go. Thank you. The first myth is the myth of perfect foresight, and anyone who thinks they can predict the future ought to work for a utility, I guess, because they need it, perfect foresight to determine what to build, when to build, and how much of what resources. Particularly those utilities that use single load forecast and base all their planning on a single future, it's unlikely to materialize in the long run. And in the long run, I mean more than a year. It's pretty hard to see out there very far. I've got a couple examples, and when you hear utilities refer to the precision or the accuracy of the forecast, they're bordering on mythology. Mike, my control's not working, so you're going to hit it for me.
Okay.
This is the first indication of the illustration of a myth. This is the annual load growth in gigawatt hours, or annual loads in the Northwest in gigawatt hours from the period 1952 through 2006. And if you look, there's a fairly normal period that goes from 1952 up to about 1975, 76. Then it sort of goes flat, and we had a recession. And if you'd looked at, put a ruler to the line there in blue before, for the 20-year period from, or 25-year period from 52 through 82 or so, 79, you would have thought life was going up pretty linearly, and it turns out between 1979 and about 1985, the loads in the Northwest basically stayed flat. So you would have been mistaken by a fair margin if you had just extended that line out, and it turned out in the Northwest we made some big mistakes by trying to build 5 nuclear plants, one of which got finished because we didn't need the other 4, and spent $7 billion and change on that mistake. So that's a fair amount of mistake. If you look, starting in around 2000, there was a precipitous drop in the Northwest loads as a consequence of markets in the Northwest driving prices up and turning industrial plants off. And if you'd extended, again, a ruler or even an econometric forecast, looking at the information contained in sort of the purple area of this graph, and extended that out to 2006, you'd have been way wrong by about 2,000 average megawatts, or about 150,000 gigawatt hours a year, or about 50,000 gigawatt hours a year in difference in load. So it's a fairly significant error, and you wouldn't have seen that even a year before, based on the prior trends of either a 30-year, or 40-year, or 50 or 20-year period. Pick your time frame. So that's just a clear indication that some humility about what might actually happen to loads in the future needs to be entertained in any forecast of future growth. Let's go to the next one, Mike.
Okay.
Econometric forecasts anticipate that the future will look similar to the past, and this chart shows the market prices in the West Coast market traded at the Mid-Columbia Trading Hub starting in February of 1996 and going through December of 2008. And there was a big spike around the spring or so of 2000, 2001, and there was no indication prior to that happening that the prices would do anything like that. They were running around $20 to $30 a megawatt hour, and people were pretty fat and happy. And so you can't underestimate the chance that things will go sideways on you, and that needs to be taken into account in looking at the future. So the myth 2 is that if you think you have a perfect foresight, you can make the best forecast of a portfolio. Myth 2 is basically a corollary to myth 1, is that there's no truth about the future, and if you think you have a single future, you're going to be wrong. So they shouldn't, utilities should always test multiple futures about load growth, because there's both load uncertainty and there's resource uncertainty. The value of doing that for energy efficiency is because supply-side resources are pretty lumpy, other than reliance on the market, which tends to be fairly volatile in price. And energy efficiency has pretty much all capital, so it's not subject to fuel price volatility. It's not going to be subject to carbon cost volatility. It has a pretty short lead time. That is, you can ramp it up reasonably quickly, and it's relatively inexpensive, so that if you buy too much, it doesn't cost you a lot to have overbuilt in the short run. This is important mostly for utilities that are vertically integrated, because the risk of failure generally are borne by their ratepayers. In competitive markets, overbuilding risk tend to be borne by the merchant plant developers who can't sell into that market. So that this is less important in terms of the concerns for the open markets or competitive markets. Myth 3 is that econometric models can forecast the impacts of energy efficiency programs, including codes and standards. What they can do is forecast what the impact has been on the past, because they embed whatever happened in the past going forward, because that's the level of impact codes and standards have had in the past. The econometric models are estimated on that time frame data and the relationships that existed back then, so they extrapolate those forward. This really creates a potential for double counting, the opportunity for improvements in efficiency above and beyond what codes and standards have brought us in the past, or whatever level of market improvement has occurred in the past. So one has to be very mindful that there's a large opportunity for double counting savings in a resource potentials assessment if the underlying efficiency improvements embedded in the load forecast aren't accounted for. Let's move to the next one, Mike. This is one of my favorites. We can't forecast loads in the future, and it's unlikely we can forecast market adoption very well of energy efficiency from an achievable potential standpoint. Many micro models of the universe assume that there's a fixed relationship between the incentives offered to a person and their ability to take that measure up. As Mike pointed out, there are a sizable number of different barriers to improving efficiency and for people to adopt them, and not all of them relate to the first cost barrier. And some are information related, some are the prices don't matter kinds of questions. And assuming that it's only an economic choice is really dealing with a limited set of parameters. Decisions are made much more complex in the marketplace than simply the cost of a commodity or efficiency improvement. The other element of this is that a secondary problem in using these models is that they're used to develop incentives for consumers, so that the people trust this economic modeling, so that they offer a 50% incentive. They presume that 50% of the consumers will take that measure. Program designs have demonstrated that the incentive levels are only one part of consumer adoption. The ease of program participation and lots of other things need to be taken into account in terms of proving program participation unrelated to price. So we're at treating energy efficiency a resource, another myth. If you hear the statement, as I pointed out here, that we can't get to more than 50% of the consumers because we're not going to pay more than 50% of the cost of a measure, you've just seen this myth unfold. They're really not treating energy efficiency as a resource because in fact, you could pay up to 100% of a cost-effective energy efficiency resource and actually pay more than that if necessary, if it's still cheap, still lower than avoided cost to buy that measure. My analogy here is if you offered 50% of the cost of a new generating resource and you got only 50% of GE's output of a new combustion turbine, then we might have a parallel universe, but we don't. It's not likely that vendors will supply new generating resources for half their cost. We should not expect consumers to supply energy efficiency for half the cost of getting it done if it benefits the utility. On to mix 6. This is one to take to the bank, is that both Mike and I think that achievable savings are usually underestimated and rarely overestimated. If you look at the difference between tech and economic potential, you see that there's not much economic potential. That's an error in and of itself. There's usually a huge amount of economic potential in any market. The Northwest has been doing energy efficiency for 20 years, and we've got double the amount available that we did in the last 20 years, still available in our supply curve going forward. So even though we've done a lot, there's still more to do. The next major myth is that there's a big write-down between economic and achievable potential. It's pretty well been demonstrated that we can get at least 50% of the economic potential, probably closer to 65 over a 20-year period. You can't get it all next year, but you have lots of tools available to utilities and political tools available through codes and standards to achieve fairly large fractions of what's economic to achieve. The Hood River project, in a 2-year period, we've got 93% of the potential savings achieved over a 2-year period by weatherizing homes in that entire county. And the council looked back over the last 20 years to see how much of what we thought we could get in the first plan achieved by the 20th year, and we got well over 85% of pretty much every measure that was assumed to be possible to achieve in 1983. We'd gotten to those measures by 2003. And there's documentation available. There's a link there that you can go for citations to those two projects. Only net savings matter? Well, they matter from the standpoint of benefits per dollar invested by the utility, but from a power planning perspective, gross savings are what count because they're the entire load. That entire load offset is what the utility has to meet as a residual load. So if the meter turns slowly for whatever reason, it doesn't matter whether the utility caused it, whether codes and standards caused it, whether the consumer adopted that measure on its own. The net load after all those things have taken place is what the utility has to generate resources. So if you're not dealing with savings in the end, then the power planners are not very interested in the total or in the net because they see the total. That's also true for greenhouse gas emissions. All reductions, whether net or gross, reduce greenhouse gas emissions. So the total gross savings offset greenhouse gas emissions, and so they need to be counted as the total emissions offset. Behavior trends, I think Mike ought to take this one on.
Sure. One of the things that was sort of a dogma in California throughout the 1990s is that you can't really model behavior. You can only look at, firm investments in more efficient equipment. And when the crisis came about in California and there was all kinds of problems with respect to both availability of plants and pricing in the wholesale market, it turns out that retrospectively the biggest energy efficiency resource was just customer response to public marketing and appeals to reduce consumption during peak hours. It was the biggest, quote, energy savings program during the crises of 2000-2001. Of course, there's an argument still raging in California about whether that short-term behavior, which we saw, in some cases, households reduce their consumption by anywhere from 5 to 15% online in aggregate, whether that would become a long-term habit or just as a short-term behavior. And currently in the California forecast, they assume that roughly 50% of that behavior change stayed and can be seen and observed in terms of lower usage, and the other 50% was just, a short-term response to the crisis. I think in part out of that experience, as well as just more experience with social networks, now some of the most interesting programs that people are looking at in terms of motivating customer behavior are not incentives, but social marketing programs that seek to influence long-term behavior. And we're only now beginning to try to model the impact of those programs within forecasting models by looking again at, whether you can solely use economic criteria to define what fraction of the populace would respond to any particular program or buy a particular measure. And what we found in doing these assessments is that you really need to have control groups so that when you're looking at changes in behavior to a particular targeted set of individuals who are part of that program, you really need to understand the control group and whether or not they have access to that same social marketing message, whatever it might be, in order to effectively estimate savings. So bottom line is behavior does matter. The real question is, can you accurately model whether changes in behavior will become habits? And I'm going to cover the last two myths here. Myth number 9 is still controversial. In my career, there's been 3 resurgences in the sort of snapback effect literature, and I think it's just starting again. Most of these models assume that the cumulative savings achieved either at the household or at the customer level are not related to the growth in energy service demand. In other words, there's essentially no real snapback effect. And I would say that based on what we've looked at, the snapback and income effects can be large or small depending on the nature of the purchasing process. In many cases, there's not a lot of discretion involved. For example, if you save a lot of energy from your refrigerator, you're not necessarily going to go out and buy a bigger refrigerator next year. But in other cases where, for example, in California, the building standards have reduced the effective, energy bill related to heating and cooling rather substantially over a 20-year period, one can argue that that was at least a contributing factor towards the fact that Californians now buy much larger single-family homes. And I've seen some analysis that suggests maybe up to 30% of that increase in typical size from around 1,600 square feet in the 80s up to like 2,400 square feet per typical home in the 2005 to 2010 period was due to this essentially additional disposable income that was available to customers. But of course, it's difficult to separate that effect out from all the the effect of cheaper financing and other types of loan processes designed to get people into bigger houses. So the lesson that we learned here is that there needs to be some kind of interaction between increased disposable income and energy service demand, but we really haven't figured out how to do that yet. And I'm getting to the last myth here is that energy efficiency programs cannot significantly reduce load growth and defer resource additions. And as Tom has pointed out here, there's ample evidence to the contrary that, in fact, efficiency programs have significantly reduced load growth in many jurisdictions that have had programs or a history of programs for 10 or more years. And these are just a couple of references that you can look at to confirm that for yourself if you want to go look at that. Okay, and here's an example of how energy efficiency has reduced sales growth by over 50% over 30 years. Tom, do you want to talk to this slide?
Sure. We have two plots. There are two lines plotted here starting in 1980. We have cumulative load growth plotted on the vertical axis with and without the effect of energy efficiency programs and codes and standards in the Northwest. The upper line, the red line there, is the cumulative load growth we would have seen through 2008 into 2008 from 1980 had no energy efficiency programs or codes and standards modified load growth. And the bottom line is the actual load growth that we saw as a consequence of having those in place. And the difference, if you look at the end point in 2008, basically, instead of cumulative load growth of about 30,000 gigawatt hours, we're up around 75,000 gigawatt hours and 70,000 gigawatt hours. So about half, a little better than half the load growth cumulatively over that 28-year period has been met with energy efficiency resources. So that's a fairly significant impact on the demand for new generating resources to make up 3,000 gigawatt hours is a huge amount of generating resources, on the order of about, it's 4,000 megawatt plants working at 100% output, and most of them work around 50% to 80% output, so we're looking at something on the order of maybe double that, 7 to 8 plants of 1,000 megawatt nameplate.
And Tom, let me just add, a similar analysis in California showed that the cumulative effects of all of these programs reduced sort of the baseline load growth from 2.4% projected over 20 years to about half of that, about 1.3% per year, after taking into account both programs and the effect of building and appliance standards.
Very comparable results between the two areas. I think the next slide, and you can see that the impact has been on where you've had active programs in the Northwest and California. When you look at use relative to 1980, what this plot on the vertical axis is, we used the reference year 1980 is the consumption per capita for everybody living in these regions or states, and you can look at California and the Northwest states basically having flat or declining use per capita of electricity, and states, Illinois, Missouri, and Texas, where there haven't been active programs for a long time, or in the case of Illinois, even the state building code, has not dampened the consumption growth in per capita electricity use. So, over a sustained period of time, even though there have been more people, their consumption has gone down. think it's back to you, Mike.
Okay, thanks. If I can get through this slide here.
I think every line was there, so.
Yeah. So before we go on to our top 5 strategies to try to, improve your success in integrating energy efficiency into these resource planning processes and into forecasts, are there any other myths or insights that folks on the phone wish to share about resource planning or forecasting processes in addition to the ones that you saw there, or do you have any questions about any of these myths? I'm going to pause for about 30 seconds, and then if we don't hear anything, we'll assume that we should just go on.
Can you guys hear me?
Yes.
Tom Singer with NRDC in New Mexico. I'm curious about the perception of sort of the dispatch crew in a utility towards these planning results, and I'm not sure I've seen you specifically address whether the plant managers and the dispatch folks believe these results and how they integrate the results.
Do you want to take that, Tom, or you want me to respond?
I think we both can.
Okay, go ahead.
At least in the Northwest, the dispatch folks on an operational basis are basically they face the load that they see, and so all they see is the net impact of energy efficiency over time. They don't see it as an operational reserve or anything like that, where they might see dispatchable resources, demand response or something like that for peak reduction. But the energy efficiency it shows up as a slower meter turn, and they don't really see it as something they need to respond to. If you're talking about whether the resource planners see it and count on it, the answer is yes. In the integrated resource planning processes as practiced in Northwest, they're building and scheduling resources for construction to meet the net load requirements after energy efficiency has been accounted for. And so their lead times are adjusted to accommodate the fact that loads are going to grow at a lower pace as a consequence of the energy efficiency program activity and codes and standards taking effect. That used to be a bigger problem when resource lead times were 10 to 12 years for the construction of new resources. But with wind and combustion turbines that seem to be the flavor of the day, the lead times are in the 3 to 5 year range. And so they feel much more comfortable dealing with energy efficiency as a resource because they don't have to start construction 10 years in advance to have a 1,000 megawatt generator online. So they can afford to be a little more confident that the loads won't materialize ahead of schedule.
Thanks.
So this is Mike Messenger. I want to try to address your question as well. I would first of all say that it really varies by the states we're working in terms of how much credibility energy efficiency potential analyses or estimates of savings within a load forecast have. In places like California, where people have been interacting and it's essentially trying to build trust about the credibility of their forecasts, and there's a lot of work on trying to do backcasting and improve credibility against control totals, I would say that most of the resource planners believe in the energy efficiency results as being credible, with 2 caveats. One is, I don't think most people involved in generation and transmission supply believe that you can actually defer the need for transmission investments. I think most of the transmission planners that we talk to say, look, even if you are going to reduce the level of demand we see in this substation, we think the benefit to our system of both increased reliability and increased ability to deal with distributed generation resources are worth doing the transmission upgrade regardless of what the level of demand is. So I believe that transmission planners continue to discount the results of these studies pretty much across the board. The second thing is that generation planners, I think, believe that the energy efficiency is real, but they have a real skepticism about whether the underlying embedded level of efficiency in their econometric forecasts is being double counted when you look at energy efficiency potential or energy resource potential standards. They need to be convinced and we just went through a 12-month process of convincing people in California that there was not any duplication of the embedded savings in the baseline load forecast versus what's in the energy efficiency projections. So with those two caveats, I think that, on balance, if I had to guess, probably 50% of the resource planners believe well-documented energy resource planning projections, but it still hasn't translated into a deferral of transmission investments. It's mainly been generation resources and generation purchases. So with that, I think, unless there's any other questions we should respond to.
Yeah, we got a couple, Mike.
Okay, go ahead.
One on the impact of appliance standards on programs going forward, particularly the more recent agreements that have just been reached with AHAM and the HVAC industry, AHRI. I think those are fairly major changes scheduled to take place if DOE adopts them to go into effect. The lighting standard in 2012, 2014, the appliance standards in 2013 to 2015, and the HVAC and furnace standards in 2013 to 2015. All of those are fairly major improvements, and also the commercial lighting general service fluorescent standard, linear fluorescent standard, go into effect here in the next year or so. All of those will require major changes in program delivery and design to reach the next level of efficiency and stretch to higher levels of performance in each of those markets. The virtuous thing is that as appliance standards and efficiency standards go into effect, they're going to dampen load growth more than any of the voluntary programs operated by utilities will, because they reach since these are manufacturing standards, they'll reach 100% of the market with their impact, as opposed to some small fractions of utility programs. So one can anticipate that the fractional load growth over and above fractional load growth impact will be more than the anticipated impact of programs were going forward. So we'll have to redesign programs, but the net load additions will be much smaller than we would have been able to create via programs. I think there was one other one, maybe two.
Yeah, let me try to take a couple of those. So we have two questions. One has to do with what's the impact of standards in terms of how it's going to affect programs and whether it will make it more difficult to achieve savings over time for utility programs. So I'll address that one in a second. And the second one has to do with, when can you count on, or how long out should you count on continued program funding? Because IRP planners tend to say, well, maybe we can count on funding for energy efficiency programs for the next 3 years, but beyond that, it's kind of speculative. You could get regime change, or the PUC could decide not to fund the programs anymore. And so basically the thrust of that second question is, how long should we rely on funding projections, and how soon do they become uncertain with respect to resource planning? So let me deal with the first question first. I think it's basically best practices now, particularly on both coasts, the West Coast and the East Coast, for utilities to work hand in hand with the people who develop codes and standards at the building level as well as at the state level as well as at the national level, because they see utility programs as essentially providing support to testing some of these emerging technologies and bringing them from the laboratory into the marketplace, such that once you hit a market share of anywhere from 1 to 10%, then you can consider those particular technologies for both programs and ultimately standards. And the real significant, I think, public policy breakthrough has been people saying, well, utilities should be able to get credit for some fraction of these savings that ultimately come from standards if they are involved in the development and testing of equipment that ultimately becomes part of the standard. So I think that's the way to deal with that uncertainty. In terms of dealing with the uncertainty about program funding and how far out can you count the conservation resource as being real and credible, experience suggests to me that once you get beyond 3 years out, it's difficult to count on a specific level of funding and therefore savings to be available. In California, what they do is they split it up between what they call committed savings and uncommitted savings. And committed savings are anywhere between 2 and 3 years out, where they're reasonably sure they've got a program design and funding approved, and they count those as completely 100% committed and credible within the process. And then for uncommitted program savings, which might be from, let's say, 2013 on, people assign different probabilities of success that funding will still be there, and you'll get the program savings that are forecast from 2013 to 2020. Tom, can you talk a little bit about that for the Northwest? How far out do you consider the projection to be credible and certain that it's going to actually happen? Is it 2013, 15, 20?
Well, in at least 2 states, there's a biannual requirement to redo their integrated resource plans. So each resource plan has a new result and a new action plan associated with that. So it's possible that you can get. I don't think you should expect major swings in efficiency nor generating resource development every 2 years, but they get reviewed every 2 years, and so you've got certainty at least for a 2-year period, but no longer. I would anticipate, and haven't seen things move around in the last 2000. Things have been pretty well. Gravity has forced the efficiency investments. The gravity of resource cost on the other side has forced the efficiency investments to be pretty sort of taken as given that we're going to be at a certain level of investment and growing, and that's been true for a decade now. That wasn't true for the first 2 decades. We had, as Mike said earlier, a fairly Mr. Toad's wild ride of investments up and down, but it's been sustained, and I don't see that diminishing in the foreseeable future. But IRPs uncover new information, and you might change the level of investment. If get bottled fusion out there, we might see a difference of opinion.
Hey, Tom and Mike, this is John Wilson. I posed that question. I actually had a little different slant on it, which was, if you look at a typical program life, it's going to be about 10 years. So after 10 years or so, you're going to start to see the anticipated savings erode. And so in a resource planning context, if you sort of said, okay, well, we can only count on 2 or 3 years of programs, then after the 3rd year, 10 years from that, you're going to start to see program erosion, and you're going to say, and the resource plan is going to say, aha, we need to build a new power plant. But of course, in reality, you're going to have new programs coming along every year. And what I was asking was, where you've got a situation where a program is likely to sort of play out, likely to replace all of the current generation of lighting with new lighting. I have seen a lot of planners in other regions sort of assume programs beyond that, and I would say what the state of the art is in terms of that, because we have resource planners in the Southeast who are saying basically, once you get past what we've got on the books, there's not going to be anything else. We can't count on anything else.
Yeah, in terms of the Northwest plan for the region, we look out, our plan has to be 20 years by statute and 5-year intervals between them. And so we have an action plan that covers 5 years but extends for a full 20 with anticipated efficiency development and other resource development spanning that 20-year period with identifiable resources. Because the way we do IRP, we have supply curves, so we can say, hey, these are commercial building savings, these are industrial, these are ag savings that go out that 20-year period. These are from retrofit, these are from new construction. And so we have a resource stack going out 20 years. It's refreshed every 5. And that's true of pretty much all the utilities in the Northwest that do IRP under their state requirements. They're at least 10-year time frames and typically 20. And I don't see that behavior where they're saying, unless they've exhausted the economic potential or achievable potential, I don't see them saying now's the time, we can't count on it. They're building it into budgeting processes going forward, saying this is the cheapest thing we can do by a factor of 2 or 3. So the commissions have pretty much said, we anticipate that base level of funding needs to be there to buy this cheaper stuff first, and if you need to go and build generating resources to supplement that to meet load growth, we'll take that on a case-by-case basis. So there's a prudence review that goes through, but I haven't seen, at least in the Northwest, a cliff out there where they say, can't count on it past that point.
So John, this is Mike Messenger. I also wanted to comment on your question. It seems to me one of the most controversial parts of load forecasting with respect to energy efficiency these days is what to assume as the replacement decision in the next generation of energy efficiency equipment. And this gets to your question about how long things persist. So let me just give you a case example. If someone invests in a CFL in program year 2008, and that bulb goes out in 2011 or 2013, whatever, do you assume that customer reinstalls a CFL, or is he going to go back to his, quote, habit of installing it incandescent? And if you assume that they install a CFL, that they've sort of learned that behavior of buying more efficient light bulbs, do you credit that to the program, or does that become naturally occurring? And I think that gets to the gist of your question of what happens after the program starts to run out, and can you expect customers to continue to invest in the kinds of energy efficiency things that they've done in the past or not? Currently in California, they assume 50% of the customers will reinvest in the CFLs, and the other 50% have to go through the same economic choice algorithm to decide whether it's cheaper to buy the CFL or purchase an incandescent bulb. But that's just based on a couple of very small studies. And I think that's an area that a lot more research needs to go into, is that what happens sort of after the party and after you've received rebates to do an efficient system. Are you likely to invest in the same level of efficiency or more in the second generation?
Well, that's a very helpful answer. I think, though I'm getting at something a little bit more maybe esoteric from a resource planning point of view, but really important when you think about the implications of resource plans and long-term investment decisions, particularly when you're looking at capital investments in power plants that take 5 to 10 years to realize. And the question is sort of, how do you model a hypothetical efficiency program? So when the CFL replacement program is played out and the entire state has adopted CFLs as its baseline technology, is there the next generation of lighting efficiency that you might model? And of course the answer is, well, we don't know what that looks like. It might be a super high efficient LED, or it might be something else that someone's inventing somewhere today. And so the question is there sort of a state of the art? And it sounds like from Tom's answer is in the Pacific Northwest, they are modeling sort of hypothetical efficiency programs all the way out through 20 years.
Yeah,
whereas
the way we're doing that is, because we have granular supply curves, that is, residential weatherization, residential appliances, commercial lighting, commercial HVAC, and you can do this either with IRP or you can do it with energy resource portfolio standards that Mike talked about. The critical ingredient is having that detailed assessment of potential, so you can posit that programs attacking this market or that market could produce some magnitude of savings at some known cost. And that's what you're really modeling. You're modeling these as little generating resources that don't generate, but on the generating side, they're speculating as to what the new wind project or the new coal project or the new nuke project, in your case, or the new combustion turbine might cost. They haven't got it ordered from GE yet. And so it's no different than speculating on what those might cost sometime 5 or 10 years out. So I think you don't have to have the program design in mind to say that there's a potential for doing that. And if you have enough history around the country showing that it is possible to go get that market, and there are pretty much examples everywhere for doing that there's no reason to believe that someone couldn't mount a program to achieve some level of that savings.
So the critical step here is granularity of the load forecast and the potential assessment.
Yeah, you need to be able to point to real things. If we install so many ground source heat pumps or we install so many high-efficiency air conditioners in so many houses, it sums up to this much load offset. And
right.
You can't point to that level of granularity by saying, well, we're just going to take 2% off the top. Well, with what? And then the argument becomes really a much more philosophical debate, because you don't have the evidence to say, well, I counted up these 18 different measures and they totaled so many gigawatt hours a year of offset.
And so if you've got then a situation where you're saying, yeah, sure, right now we can't go after all of that potential because it's not all cost effective, but by 2020 we might assume that the cost will come down, and so we can go after a bigger chunk of it. So it's there, and we can.
There's enough out there now without even having to go to that's cost effective under current headlights. I mean,
right. But that gets to the issue that I brought up before: is what's your forecast of the current incremental cost of all measures, and what's your forecast of what that's likely to be 10 years from now? And the conservative assumption that I think used most places is that the real cost of efficiency is not going to go down, and so we just need to forecast on a scenario basis whether, for example, there's going to be LED programs or other kinds of advanced technology programs. But what I'm suggesting is if you go back and look at the incremental cost trends over time, in some end uses and for some types of technology, particularly for lighting, you can develop a forecasted incremental cost that declines over time with reasonable certainty, and then it's a simple multiplier effect to try to figure out, okay, well, if the incremental cost of the program is X, what are the necessary program and program design costs to accompany that, and is that cheaper or not cheaper than a supply option on the margin in the year 2020? And so that's where the judgment comes in is, are you willing to accept that, the program costs are going to add another 40% of cost on top of the incremental cost, and that's the total delivered cost in the year 2020 or not? And I think practices vary by jurisdictions about whether they allow these so-called emerging technologies that aren't cost-effective today to be included as part of the forecast of likely sales or the forecast of ERPS.
Okay, thank you.
Sure. I think because of time, we're going to have to try to finish off and go to our strategies and best practice, and then we'll save the rest of the questions for the end. There are a couple of really useful questions about, to what extent can we standardize some of these practices, and we'll get back to those just a little bit. So, Tom, I think you're going to be up next in terms of discussing both where to intervene in resource planning processes and your top 5 strategies.
Okay. Hopefully my cue card will work here. I've got a couple points here in terms of intervening in the IRP processes and where resources are considered. I think you need to be strategic about who's making what decision and about whether the models that they're using are compatible with one another. I hearken back to where the load forecast model is totally separate from the energy efficiency supply assessment, and if those are headed down different paths, if they're not integrated, that you've got a set of decision makers that are completely isolated from one another, that don't talk to one another, and so you get one forecast of numbers of units and usage, and another one completely independent of that, and that path just doesn't lead to anything productive. I think you've got to insist on how a description of how they're going to integrate the energy efficiency assessment results into the baseline forecast, so that the level of efficiency assumed in the baseline forecast is a known entity. As Mike and I pointed out, the econometric forecasts don't have enough detail in them to tell you typically what level of efficiency at the end-use level is assumed, so you don't know how much technology improvement they assume in the baseline forecast. And if it's embedded there, there's a real chance for double counting the potential benefits of energy efficiency. If it's not embedded there, you can't tell. And so that really limits your ability to question whether the underlying load growth that's anticipated includes energy efficiency or not. And you need to be prepared to ask some fairly penetrating questions about what's assumed in the load forecast. Please demonstrate to me how you know that. And if they can't do that, then continue that line of questioning about, then if you don't know that, how can you tell me how much is left to do? And that's really critical, a critical set line of questioning. I think if you look at the guide for conducting, I've got a reference here, guide for conducting energy efficient potential studies, gives you a pretty good idea of what those require in terms of data and resources. One thing you should never do is to believe the black box results of achievable potential. If you see achievable potential written down more than 50% of economic potential, then you have the right to call bogus based on lots of information that's available that says we can be pretty well assured of getting at least 50% of economic potential, and probably a lot more than that, particularly over a longer period of time. There are lots of IRPs to point to where we're getting at least 65% and up to 85% of economic potential is identified as achievable over time, because you have multiple mechanisms, including paying for most of it and getting it in codes and standards. You have to be temper that with depending upon what is included in the target. If codes and standards and a budget cap is limiting the ability of the utility or the systems benefit administrator to achieve things, their target is based on net savings and it's based on savings independent of codes and standards, then the argument of getting to that level is a little more difficult. I guess.
Okay, I'm going to chime in here with, based on all this discussion we have, I have 5 strategies or recommendations if you're interested in trying to effectively integrate program savings forecast into demand forecast, or for that matter, IRP, Integrated Resource Planning. You should try to work with whoever is organizing the public process to develop this plan to make sure that there's an explicit identification of the uncertainty of all inputs to the forecast, and hopefully on a probability basis, not just the ones that you use to develop energy efficiency program savings forecast. We have lots of experience where we come in and show probabilistic assessments of energy savings, and then everybody else is treating the forecast of like households and demand for specific appliances as a given and not varying those things. Sophisticated models allow you to vary the inputs, the uncertainty around inputs systematically using Monte Carlo, and you should insist on that both on the demand and the supply side. The second one I've mentioned already is it's really important to require a comparison of backcasts of program savings from the model to see to what extent that the savings that have been modeled actually reflect actual sales for a historical year in 2007 or 2008. The third thing is to have a discussion of the possibility of systematic bias, either high or low, for the people who are developing the inputs. We've seen that there tends to be a systematic bias for some people in terms of developing program savings estimates. They always assume they're going to be towards the higher end, and our experience is it really depends on the jurisdiction. In some cases they're higher, in some cases they're lower. So you need to make sure that you have a discussion of that you're not systematically either being overly optimistic or overly pessimistic. We've talked before a little bit about, trying to understand what has the biggest effect on the forecast, sort of a priori. It may be that, the forecast of economic growth has a much bigger effect than details like standard adoptions or program ramp-up rates, and you need to understand that and know that. So one way of doing that is to ask people to systematically vary all of the drivers by some given percentage, 10, 15, 20%, and see to what extent that swamps or is smaller than some of the energy efficiency drivers that are modeled here, like, what are the assumed rates of standard adoption over a 10-year period, or what is the assumed program ramp-up rate over a 10-year period. And finally, one of the most difficult things to do is to try to take an evaluation load impact study and decide, well, based on this, how should we change the baseline forecast? And one of the things that we see done quite often is people report savings out of context. They'll say this program saved 625 megawatt hours, but they won't say over how many buildings or for how many households, over what end use or what number of appliances. And until you can normalize that savings to a structural unit or a level of energy service demand, you really can't compare and use program evaluations in a program load forecasting context. So it's important to try to have standardized formats for providing context for energy savings results. So those are my top 5, and I'm going to turn it back over to Tom.
Okay, my first one is that it's going to take money to do this right. I'm a firm believer that in order to do a realistic job of assessing potential, you need to spend a considerable amount of money getting customer characteristics and doing planning and evaluation to get the bottoms-up work done. If you look at Cemetery here, when they look at new generation resources, they spend an awful lot of money doing site investigations, determining where the wind blows, where the coal is, what it's going to take to get a gas pipeline to a new generating resource site. And comparable amounts of money need to be spent on energy efficiency to develop the data necessary to plan that resource. And I think one can argue that in the interest of Cemetery, we need to spend comparable amounts of data to develop enough information to determine how big this resource is, what it's going to cost, and how long it will take to develop. My second point is I'm a firm believer in energy efficiency savings goals, not expenditure targets. It's really easy to measure expenditures, but they don't always result in energy savings, or at least they don't always result in cost-effective savings. So holding people's feet to the fire on saving kilowatt hours and kilowatts or therms is much more important than spending dollars. Make sure that you've got a report that you can read annually on progress that says, here's what we spent and here's what we saved. Not just here's what we spent, nor just what we saved. You need to compare the cost and the benefits, and you need to have a regular report that sees the light of day, publicly available, that provides detailed information on where the savings came from and how much it cost. And that has to have some stakeholder involvement in review. Focus on gross savings, but don't forget about the net program designs. Planners really care about gross savings, as I said earlier, because it's what the net result of that is. You've got to plan resources to build the residual to meet the loads after you take gross savings off the table. But in program design, you need to pay attention up front to what you think the net effects are going to be, so you don't design programs that are redundant with the market. If you see net to gross assessments that 80% of the gross savings actually disappeared and you only got 20% net, then something was wrong with that program design to begin with. They were going after things that the market was already doing and wasting lots of money. So up front, pay attention to that in where you think they're heading for the market, and so that you actually see beneficial expenditures of dollars, and pay less attention to the gotcha game after the fact, because that leads to fairly large levels of animosity amongst the players. Mike, I think we're back to you.
Thanks, Tom. Okay, so we're just going to try to review now sort of the key best practices that we discussed in the last hour or so. The best practices that Tom and I both agree should be thought about when you're intervening is there needs to be some form of public discussion of all the inputs in the key program savings inputs before the models are run, discussion of the uncertainties, and an explicit discussion of the potential problems associated with linking exogenous savings forecasts with other types of econometric models. We've talked about double counting already, and an explicit discussion of attribution or causality, how it happens in the forecasting model and how it happens in the energy efficiency resource assessment. You need to make sure that they have relatively similar processes, otherwise you're mixing apples and oranges. One of the things that's been controversial in California and other places is you have to ensure that there's some interaction between forecasted changes in the building and appliance codes and that the program savings are handled consistently. And what that means is that if a standard takes effect, that its savings are counted first, as opposed to assuming that the utility program that might have been there for 2 or 3 years previous to the standard continues to get credit for those savings when in actual fact the law now requires everybody to just buy products that are at a minimum efficiency level. And to be clear on the attribution methods for public policy initiatives, you know, in California there was some debate about, well, in the loading order, if you have programs simultaneously competing, a local government program, a national, Energy Star labeling program, and a national appliance standard program, which has, first dibs in the attribution or loading order, and it was resolved in this particular case that the appliance standards had first bracket and labeling programs second, and finally local government programs. Okay, so now the summary of, what are the public policy uses of all the energy efficiency forecasts that we've been talking about? Basically, I'm going to go through these last 4 slides quickly so that we can get to your questions. They can be used as energy efficiency policy benchmarks, comparisons between program types and administrators, comparisons between savings and the underlying forecast. They're also used as inputs to development of performance compensation mechanisms for utility program ministers, and obviously they're used for overall assessments of cost effectiveness at the portfolio level. Tom talked extensively about how they're used in public policy with respect to resource planning, both assessments of risk and likely cost of different. They're used to help target programs and make decisions on the timing of certain resource procurement or contracting processes. And finally, they're used in program planning, and I actually think some of the most beneficial uses of these energy efficiency potential forecasts are for targeting of market segments and end uses at the program planning level. They assist in budget planning and can help with adaptive management of programs. When is the program likely to become redundant with what's happening in the market or codes or standards? Does that mean you should shift money towards more explicit coordination of emerging technology programs and coordinate that with the likely anticipated standards dates? Those types of considerations. And finally, they can be used, and they currently are used in many cases in climate change analysis. To what extent will energy efficiency reduce sales forecasts and therefore reduce the amount of renewables that are needed through various RPS standards? They're also used in many cases to try to figure out, is it feasible to actually reduce GHG emission trends, which appear to be heading upward in many of the industrialized states, regardless of the level of programs that are happening. You can also use these forecasts to assess the interactions between sectors that aren't very often looked at. Buildings, utility, and transport sectors is one that's currently being looked at in great detail because there are some interesting interactions between buildings and transport that haven't been explicitly modeled in the past. Okay, final summary, and then let's get to the questions. There's two primary approaches used to estimate the level of resources that should be procured or funded. Each has its strengths or weaknesses, and as I think Marty pointed out earlier, you could in theory do both, but in practice, people either use the IRP approach or the Energy Resource Portfolio Standard approach. I haven't seen too many states where they're both going on simultaneously because you might have both coordination problems and just not enough funding. The choice of these, I think, depends on the dollars available and a lot of institutional history. Some organizations forecasting organizations have collected a lot of end use and customer level data, so that tends to lend itself better to using it in an IRP process. Others don't have that much data that's actually been collected, and they tend to head towards energy resource performance standards because it's easier and you don't have to collect all that data, at least in theory at the beginning. The biggest uncertainties that we've outlined are the integration of these exogenous savings forecasts into forecasting models, both used for resource planning and just explicit forecasts of sales and peak demand over time. And we're hoping that advocates use this knowledge to reduce the need to raise rates and potentially increase environmental impacts by ensuring a reasonable level of efficiency resources are considered and included in the electricity planning processes at your state or region. So that concludes our formal process and webinar. And I want to go back and answer some of the questions. Tom, I think there's one here that you can take first, and then I'll go. There's an assumption that Moody's and others are expecting consumers and PUC to start to push back to steadily increasing bills, not rates, and that's going to be a real challenge for utilities. And the question this gentleman has is, what level of detail, re the integrated resource planning process, customer information, energy efficiency assumptions, does it make sense for utilities to share with everybody, with shareholders, and what should be considered proprietary? And maybe you can talk about what both public knowledge and proprietary in the Northwest.
Yeah, I think in an IRP planning sense, planning framework doesn't result in rates. all it determines is revenue requirements and how that cost gets distributed out to individual customer classes and how that gets distributed within customer classes with demand charges and energy charges and other kinds of fees is a fine art where the commissions have a great deal of fun defending one person's equity over another person's fairness. I think what you can expect reasonably out of an IRP is a forecast of what the total revenue requirement for the utility is given the resource acquisitions that it's going and operation of its existing plant that it's anticipated to do under its preferred portfolio. And it's important when they do that calculation that they identify sort of what the typical annual revenue requirement per customer class might be or per customer might be. So you can see the impact of energy efficiency and alternative resource strategies on the total bill. Because if you've got to distribute a smaller total bill amongst all customer classes, that's a good thing, even though individual rates might go up because you're selling less in the case of energy efficiency. What you want to look at is the total bill. So if you don't get them to give you an analysis that shows the total revenue requirement of each portfolio and only they show you the rate effects, then you don't have the right metric for either you or the PUC to look at, because we're talking about distributing a smaller amount in the case of energy efficiency because we're buying less new resource at a lower cost. So in every one of the analysis that we've done up with a lower revenue requirement long term, which means translates into lower bills. In the case of efficiency is a major component of the portfolio relative to other resources. And you can even do that on an annual cash flow basis where you're looking at, here's the total bill. As we build energy efficiency resources into the portfolio, here's the total bill if we were to acquire generating resources in lieu of that amount of energy efficiency. And you can see that there's usually on the order of a 2 to 3 year time frame where bills are higher in the short run as you ramp up energy efficiency and much lower in the long run as energy efficiency gets deployed and total consumption goes down and costs are lower. So they need to expose that much. I would not anticipate that they would necessarily expose how this is going to translate into rates because that gets determined after revenue requirements are arrived at.
Okay, and this is Mike Messenger. I'm going to take a shot at answering that question from a slightly different perspective. One of the things that we're often asked to do after we prepare efficiency potential assessments for a state or a utility is to decide what level of data should be public and what level of data should be proprietary. We tend to err on the side of we think it's important to show people at the utility all of the information about customers by sector and what the range of, the distribution of bills and the distribution of energy use intensities per square foot are. But our experience is that the utilities say that's fine for us, but we prefer not to disclose a lot of this information about, for example, the composition of industrial demand and the energy use intensities therein, because we think that's proprietary and some of our customers might be upset. So bottom line, I think you should try to disclose as much as you can because it helps the program planning process and it helps advocates understand what the potential are. But there are some legitimate privacy concerns, and we often end up redacting information about commercial and industrial sector consumption because of fears that privacy concerns will arise. I think we have sort of one other question that I'm interested in getting Tom's perspective on, and then I'll chime in. And that is, there's been a lot of different energy resource portfolio standard assessments and a lot of IRPs. And the question is, to what extent have these two processes resulted in sort of more standard models that could be standardized at the national level and perhaps save money and make it easier to do some of these assessments in states where it hasn't been done before? Can we standardize this practice? Are there, universally available models? And then I think the second question is, can you extrapolate from neighboring states? And for example, if you have a potential study that's been done in Pennsylvania, is that good enough, and can you transfer those results to Maryland? So, Tom, I'll let you take those questions first.
Well, I don't think while there ought to be there's a fairly standard methodology that one can pursue to do the energy efficiency resource assessment. Mike, when I couldn't get online here on the audio, Mike went through our 6 steps. I think that's a fairly standard fare of the methodology. You start with technical potential and work your way down to total, and that can be replicated. I think it's hazardous to assume that any particular model, if you will be able to get from that, because the models tend to be proprietary and black boxy. We would like this to be fairly explicit, make assumptions available to see what's going into those models. So a model may be an overstatement. Most of these are done in spreadsheet land and ought to be transparent so that you can actually look at what was assumed to be the base case, how many units were there, did the number of units agree with the load forecast number of units, and the forecast going forward for that, for example. Can you extrapolate one area to another? I think in gross terms you probably can, but there are fairly major differences between states in the economic makeup, so you just can't say in aggregate Ohio looks like Pennsylvania or Illinois. You need to look at the sector makeup to make sure that the sectors are comparable, or that some fraction of the sector looks comparable. Because you have different, particularly industrial sector, real different mixes across the country. In the Southwest, you have lots of mines. In the Northwest, you have lots of pulp and paper plants, and the answer for both of those are really different. So you have to be careful about migrating that level of information as a wholesale assessment. Residential markets tend to be very comparable in terms of things like lighting and appliances, and less comparable in terms of heating source. And so if you can normalize for heating source and climate, the numbers are not all that different, because the housing stock doesn't differ within general areas of the country. Well, it does east to west, north to south. Within the Midwest, it's not all that different. Within the desert Southwest, it's not all that different.
Okay, and before I do the final wrap-up and the answer to that last question, I want to encourage everybody that as you leave this conference, don't just click on your browser. Click on the little red circle with the white X there, and that will take you directly to a quick, 5-question survey on what you learned from this course and what your feedback was. So now let me get to the question of, to what extent can you extrapolate information from energy efficiency potential studies between states? And I agree with Tom that you can't really extrapolate at the aggregate level across all sectors, but in some cases you can extrapolate between similar sectors and similar end uses. For example, you can do some extrapolation of residential efficiency sales levels at different states in the Northeast. But even that, to some extent, we tried to do some extrapolation of CFL results in terms of saturation, and we found that it's difficult to do that unless you control for sort of a program maturation or program experience variable. In California, where they've been running that program for 15 years, you got much different saturation than you did in Georgia, where they might have been running it for 5 years. So even for things that seem pretty likely to be comparable, if there's a much different program history and infrastructure, the results might not be transferable. So let me just ask, we're coming to the end of our 3-hour period. Is there any other burning questions that someone on the phone wants to ask? Otherwise, I'd suggest that you go back to the RAP website after this, and you can look at additional resources if you wanted to learn more about questions that we didn't answer here today. And again, I would encourage you to fill out the survey so we have an idea of whether we met your needs. So I'm waiting to see if there's any questions. Okay. I can see there are no other questions, so I'm hoping that we answered most of your questions. If not, you can always email us back. I'm going to formally close this presentation in a second. I also want to let you know that all of the slides that we presented, plus the additional resource slides, will be available on the RAP website. And I'm going to click right to the references slide because I think there's some important information here for people who want to follow up at sort of the next level. Assuming I can. So starting here on slides 97 through 100, there's both references to attempts to integrate energy efficiency into forecasts as well as links. So you can just download the report if you're interested. It has all of the Northwest Power and Conservation Council's latest work as well as the latest work at the Energy Commission and the PUC. So with that, I'm going to stop the recording and thank you all for staying on and providing a set of useful questions, and we hope that we've provided you some insight into this, what for us is our job and therefore a very interesting topic, and we hope that we've stimulated you to learn more about this topic. So thank you very much.